从我们的讲者开始讲话，开始计时，时间6分钟。Now 6 minutes will be count down by the first word from the speaker. So, are we ready? The team number 1. All right, now we're introducing the team number 1 on stage. Welcome.
Good morning, everyone. We are team number 1. So we are excited to present our title, Transforming Waste to Worth.
Carbon capture and utilization.
To produce eco-friendly biolubricants.
Yeah, this work addresses one of the most pressing global challenges, like temperature changes and resource sustainability. This can be achieved by carbon capture, bio-based innovation, and AI-driven optimization. We are a team from National Cheng Kung University. I am Shravan from Department of Biomedical Engineering.
I'm Acha from Department of Chemical Engineering.
And I'm Firman from Department of Engineering Science.
Yeah, let's talk about carbon footprint. Over the past few decades, there's like a massive increase in CO2 emissions, which are like primarily driven by like industrial giants like China, in the United States, and in India. These emissions are directly linked to temperature changes and climate sustainability around the world.
You may wonder why focus on lubricant.
Yeah, well, studies suggest that 7 to 15% of global GDP is lost annually due to friction, energy, and wear. This is like a massive impact to our environment and also to our economy. So lubricants are the first line of defense to reduce this loss. This loss can be reduced by these lubricants can reduce like friction, wear, and extend component life, and reduce fuel consumption and emissions.
Oh, I get it. So most lubricants are petroleum-based, so requiring the harmful additives.
Yes, this is where biolubricants comes in. These are like non-toxic, biodegradable, and comparatively superior performance.
What about compared to mineral oils?
Yeah, when compared to mineral oils, so biolubricant can reduce carbon footprint up to 52%. In like a broader perspective, it can replace 30% of biolubricants, which is like equivalent to reducing 15% of global car emissions. So we can reduce like 3% of CO2 worldwide. This is like a small change with like huge impact. So let's go through our project framework. This is divided into like the 3 key components. One is like a carbon capture, and one is like microalgae cultivation, carbon fixation, and biolubricant formulation. And now we see about carbon capture. Here we use like waste materials like seawater brine, waste brine, cement slag and steel slag, and calcium oxide. So through a modified solid process, we get like sodium bicarbonate.
In the second stage, microalgae are grown using the captured carbon. The harvested biomass is then fed to flies or insects, from which refined oils are extracted in biorefinery process.
And the last part is biolubricant formulation. We combine this the refined algae with the functional additives, then using the AI modeling to analyze the formulation of molecular interaction, and then optimize the combination and get the high performance and non-toxic lubricants. But wait, what can microalgae do in this framework?
Microalgae are emerging as powerful agent in the race to sustainable development, with the ability to fix carbon dioxide up to 50 times more efficiently compared to terrestrial plants. By integrating proper bioreactor design, we can channel this captured carbon into valuable outputs from biofuels and feed to pharmaceuticals and supplements. The great news is efficiency doesn't stop there. With the integration of CRISPR technology, we can push microalgae potential even further. CRISPR has been awarded Nobel Prize and claimed as a versatile gene editing in microalgae. By editing genes involved in lipid metabolism, we can push lipid production in microalgae by 70%, turning sustainable biology into scalable industry.
So how can AI play a vital role?
Well, we feed the AI with the data from oils, addictive, and microalgae chemistry. Then, then identifies the structural pattern like the formulation of the graphene or the diamond layers which are critical for enhancing the performance. Then the AI use is predict and optimize to find the best combination to achieve the maximum lubricant efficiency and the minimal environment impact.
So in the waste to wealth, you can see this like a true circular process. Here we use like waste materials and get like a sodium bicarbonate. This is used like a carbon source for the microalgae.
Microalgae grown using the captured carbon give us valuable oils. We proceed this into eco-friendly biolubricant, commercialize them, and feed the waste stream back into the cycle.
Nothing is waste. Every byproduct is recycled or reused. This project is a perfect example of the singular economy in action.
We capture carbon, reuse waste, generate high-value green product, and reduce dependence on fossil resources, all while lowering emissions.
Yeah, in conclusion, our project isn't about lubricant. It's about rethinking like a waste, reimagining our process, and creating a truly sustainable future. Absolutely.
Thank you. Thank you, team number one. Thank you. Now followed by team number two. Please be ready.
Good morning, judges. I'm Dave, here to introduce our new hybrid technology, which transforms waste into clean aviation fuel. We are a group of 8 members, and we specialize in green fuel technology and economics of process integration. We know that climate change is a major concern due to the greenhouse gases, and transportation is one of its major sources. Aviation alone contributes to 11% of the total carbon emissions and has the highest CO2 emission per passenger kilometer, mainly due to its reliance on fossil fuel and related carbon footprint. So, is the future of aviation completely dark? Not necessarily. Sustainable aviation fuel is derived from biomass, has high combustion efficiency, and low carbon footprint. Many countries have already started to blend SAF with fossil fuel to promote circular economy and reduce emissions. This makes SAF a multi-billion-dollar industry today. Let's look at Taiwan. It has already started to manufacture SAF. But the demand is quite high than its production needs. One major reason for this is the low availability of domestic feedstock. Let's understand this better. Taiwan has 3 major airline companies. Combined consumption of fossil fuel approximates to 6.6 million tons annually. With the current SAF policy of 2% blending, they require around 0.17 million tons of feedstock per year. And this opens new prospects for researchers like us to find better feedstock and develop processes favoring the local economy. But people might ask us, what is wrong with the conventional SAF process? Why don't we just scale up? Well, there are numerous problems. First, they are designed to process a single kind of feedstock. This limits the production potential. Second, they're hydrogen intensive. If the hydrogen used isn't green, then we risk increasing the carbon footprint. So, keeping in mind the goals of net zero emission and net zero waste, we propose the hybrid pathway. It is designed to utilize solid and liquid waste simultaneously, requiring lesser hydrogen. Our problem-solving strategy first focused on using waste plastics and waste cooking oil as the feedstocks. We later upgraded to a pilot scale, and these data were then used to model the entire industrial process using Aspen Plus simulation software. We not only optimized it in limited time, but understood the economics and validation with absolute detail. So, rather than designing a new sophisticated technical process, we focused on making the existing system efficient and energy optimized. And hence, we added the hybrid technology in the sidelines without changing the existing system, making our technology feasible and ready for application right away. We have divided the process in 6 green zones. Let me explain them one by one. In zone 1, we use waste cooking oil with methanol to produce FAME, fatty acid methyl esters. This FAME is then sent to zone 2, where oxygen is removed and simultaneously the long chain alkanes are shortened to short chain alkanes. This selectivity is carefully ensured by synthesizing the active sites on our catalyst. And in presence of hydrogen, it produces the HEFA. In zone 3, we apply pyrolysis on polypropylene, which in presence of hydrogen in the hydrocracking reactor produces the PP SAF. The PP SAF is mixed with HEFA SAF to produce our hybrid SAF. As we saw, our whole process requires a lot of hydrogen, and this hydrogen is generally outsourced by conventional industry. But we solved by using the byproducts of our zone 1 for methanol and glycerol steam reforming. This is a cost-effective solution. If we look at the results, our hybrid SAF not only complies with the ASTM results, but also is better than traditional Jet A1 in some key areas. If we compare our hybrid SAF to other green fuels, it reduces carbon emissions almost by 50%. Let's look at the process results. A conventional process produces around 8.747 kg of CO2 per kg of fuel. Other green fuels reduces this value by 66.27%, but our hybrid SAF is one step ahead and reduces this value by 91.6%. But overall, we can say that our hybrid SAF not only reduces CO2 emissions, but assures flying net zero. Hydrogen consumption is another key important area. Our consumption is almost similar to other green fuel industries, but unlike them, we have an in situ hydrogen generation unit, which, after careful optimization, produces more hydrogen than what our process requires. We actually plan to sell this hydrogen to other hydrogen-intensive sectors to generate more revenue for our industry. Economically, hybrid SAF also performs well. Our feedstocks are practically inexpensive. Combined with reduced hydrogen costs and reduced carbon taxes by almost 91%, we are ready to capture the substantial market share of a rapidly increasing industry. In conclusion, we can say that our proposal is one of the first reports to diversify SAF feedstock, have an in situ hydrogen generation unit in a SAF refinery, assure great financial returns for our stakeholder, and finally, and most importantly, provide a greener, sustainable aviation sector. Thank you so much.
All right, thank you, team number 2. Now, team number 3, please be ready.
Good morning, distinguished judge and honorable guest. We are group number 3 from the Hong Kong Polytechnic University. And today we feel very honored to be here and share our project with you. The development of a smart mini-grid system for renewable energy storage and utilization. So firstly, I would like to introduce our project background. As the energy crisis is affecting our world, it has become an urgent task for humans to pursue the carbon neutrality target. And as one of the most effective strategies, we could increase the use of renewable energy such as wind and solar power. But due to the intermittencies of the natural resource, they could always fluctuate and need to unstable power generation. Fortunately, we have a strategy. We could introduce an energy storage system and couple it with the renewable energy system. In this way, the power supply could be more stable and, of course, better meet the users' demands. So, guided by this idea, in our project, we aim to construct a mini-grid system for the renewable energy conversion, storage, and utilization. As you can see in the screen here, in the smart mini-grid system, the major components include the battery control system, the solar PV panels, the charge controllers, as well as the energy storage system, which we use the vanadium redox flow battery system as a candidate here. So after all, the whole mini-grid system will be connected to the grid via an inverter. In this case, we could transform the renewable energy generated by the wind and solar power into the stable chemical form and store inside of the battery stack. In this way, when user need it later, we could release this energy anytime to the end user. So here is a brief idea about our process of creation. Our project started with a small-scale vanadium redox flow battery stack. Then, after several rounds of optimization and scaling up process, we could obtain our final product, which is a 5 kilowatt vanadium redox flow battery stack. So on stage 1 here, we designed and fabricated a 50-watt vanadium redox flow battery stack and optimized its key components, including the electrode, the anti-corrosion connected unit, as well as the current collector. And next, following the design of the 50-watt, we further proceeded to the large scale, which is a 2 kilowatt stack. During this process, we identified some key issues that are existing during the scaling up, and we solved this issue. We applied a more regional shape and enhanced the overall structure design of this stack. So as a result, the whole mass transfer inside of this stack could be more uniform and lead to a higher efficiency. And meanwhile, we apply a thinner thinner float field inside of the stack, which can make the whole system more compact. Then, followed the success of the 2 kilowatt, we further processed the 5 kilowatt vanadium redox flow battery stack. And we finished the installation of the whole system, including the pump, pipe, as well as the electronic tank. After that, we finished the performance examination of this overall system. And according to our experimental result, it indicates that the whole system was able to achieve a very stable non-circle operation with a high energy efficiency of over 80%. So why we choose vanadium redox flow battery? And what is technical advantage? The most struggling point of the flow battery technology is its long lifespan, which can even reach 20 years. And meanwhile, since the flow battery itself can support the decoupled power at capacity, this allows users to have a higher flexibility and define their own energy storage solution. So in conclusion, the development of an efficient energy storage system is believed to be the key to the utilization of renewable energy, which can give users another flexibility, a stable power supply, as well as the reduced carbon emission. And by the implementation of this project, we believe that we have processed the flexibility of this system and shown that the mini-grid system was able to achieve the high efficiencies, good flexibility, the cost effectiveness, as well as reduce the overall carbon emission. So here comes to the end of my presentation. Thank you so much for listening.
Thank you, team number 3. We're moving on to team number 4. Please be ready.
Hello everyone, we are Group 4 from National Tsinghua University, and our topic is Link a Colorful Community, Recycling of Critical Resource from Spent Lithium-ion Batteries. Here's our all members. And this is our today's outline. Our work will focus on the scale-out part. Since commercialization in 1991, lithium-ion batteries has become essential for our daily life. However, it is estimated there will be over 11 million tons of end-of-life lithium-ion batteries in 2030. From both environmental and economic aspects, recycling batteries is important, not only because of the pollution and safety concern, but also because extracting cobalt and lithium from spent batteries is far more efficient than mining. If we focus on the battery's components, we can find out that cathode and anode accounts for almost 80% of the cost, especially for cobalt and lithium in cathode and copper in anode. Therefore, Both electrodes are worth recycling due to the abundance of valuable metal. The conventional lithium-ion battery recycling process include pretreatment and recycling process of cathode and anode. Pretreatment include discharge, dismantle, separate, and delamination. The delamination has three approaches, which are heat treatment, alkaline leaching, and organic solvent dissolution. After the pretreatment, there are three parallel options for recycling process, which are pyrometallurgy, hydrometallurgy, and direct recycling. Each of them has disadvantage listed on the right, so we try to take advantage of hydrometallurgy and direct recycling to overcome the limitation of conventional method. So our work integrates completely non-toxic delamination process and continuous flow hydrometallurgical process to solve the issue. Compared to conventional method rely on heat treatment to get cathode and anode material, we design an eco-friendly solution that can recover black mass at room temperature and has around 100% yield without emitting toxic gases. The real process will be shown in demonstration time. We further analyze the removal of PVDF. Removing PVDF is important because it will hinder material separation and can release toxic gases such as hydrofluoric acid during the recycling process. So from SEM, we can see the structure is well maintained after treatment, and FTIR serves as a strong evidence for the complete removal of PVDF. After active materials are separated from current collector, we can move on to the recycling process. In our work, we can effectively extract different compounds from black mass by using the leaching solution. And our work can overcome the limitation of conventional method and is applicable for all types lithium-ion battery recycling. And this continuous flow system is adaptable for the regenerative precursor for cathode reconstitution. And the ICP compositional result shows that the purity is over 94% and the precipitation yield is nearly 100% for beaker scale level. And for our process, we can not only separate different compounds step by step, but also produce precursor for various types of batteries, such as lithium iron phosphate and ternary cathode. And the result shows that the regenerative batteries can achieve comparable discharge capacity and coulombic efficiency to those of commercial batteries, and indeed meet the commercial criteria. Starting from a few grams of powder at lab level has now grown to pilot scale level. This picture is our real pilot scale facility. We can divide the structure into 4 parts. The solvent tank can store enough base and acid to maintain proper pH level or suitable precipitant for metal precipitation. In each reaction tank, there is a mixer to make sure the homogeneity of solution and real-time pH and liquid level meter to control the reaction through programmable logic control system. After the reaction, the mixture will be transferred to the filter bed to collect the products. So this is the whole structure of our real facility. And ICP compositional results also show high purity and precipitation yield for valuable metal in pilot scale level. After accounting for the cost, the profits for recycling black mass is estimated to be around $378,000 per ton. And more importantly, our process can significantly reduce carbon emission by 41.4% compared to ore mining because there is no roasting process in our work. In summary, we designed an eco-friendly delamination process to collect cathode and anode material without emitting toxic gases. We subsequently developed all types lithium-ion battery recycling process that can yield high-purity metal recovered from spent batteries and produce high-quality recycled batteries that meet the commercial criteria. Then we create a large-scale continuous system to meet the demand of battery materials and net zero objective. Finally, we would like to thank above agency for financial and technical support in this work. Thank you for listening.
Thank you. Thank you, team number 4. Next, we are moving on to international team number 5.
Okay. Good day, everyone. We are Team 5 from Universitas Indonesia, and we're here to present our projects titled The Flux. Okay, good day everyone. We are from Team 5 of Universitas Indonesia, and we are here to present our project titled The Flux. As now, the built environment has contributed about 40% to the global carbon emissions, and therefore there's an urgent need for figuring out how to achieve net zero building by using passive design strategies. For our design challenge, here we are approaching it through two different design mechanisms. First one is retrofit, and the second one is for new building, where our design strategy focus on energy efficient building, minimizing the carbon emission through life cycle consideration and construction. Next. Here is the concentration of our design strategy. The first one is passive heat management for energy conservation. The second one is minimizing environmental impact through material life cycle considerations. And the third one is extending construction efficiency through modularity.
And let's talk about the solutions in detail. The passive strategies begin with multiple objective optimization for the building, orientations, and also geometry to maximize the heat gain and solar capture, additional solar factor and solar envelope simulation as the base for the building, special configuration based on daylighting and thermal needs, and sun spaces which can absorb the heat during the winter, combined with earth thermal mass. And all of these passive strategies can be combined with our main solution, which is the shearing layers and the PC block construction. And here's the shearing layers one. Adopting Frank Duffy shearing layer concept, we organize the building elements into standard market sizes of multiple 1.2 meters to maximize minimum waste, and using locally sourced GLT. The layers are arranged from the inside to the outside of the building based on their life cycles. And by placing the partitions such as sun spaces, walls, and windows, passive strategies grounded in building physics can be achieved. As you can see here, the proposed structures also complies to Eurocode limits. The PC blocks can withstand 5.6 MPa of force with the safety margins of over 73%, and modal participating mass ratios approach 100%, which means it has efficient mass distributions and structural durability. And we also improved the traditional material configuration to enhance its insulation properties, structural durability, and sustainability. As you can see on the table, the main masts are constructed using easily sourced ramped earth and natural fiber as stabilizers, and which both can be naturally degraded at the end of their life cycles.
Here is the making process. So the soil for the mixture is sourced from local sites, and then the mixture is processed by the help of the community itself. For the construction, the mixture is molded into different modular blocks that you can see here, and then the modular blocks could be assembled into its framing elements and insulation modules. The modular principles make sure that the system could be easily replicated and could be implemented in different construction process. Here is the comparison of the improved system and the typical masonry wall, where the temperature difference for our proposed wall is less steep. Therefore, the condensation risk is very minimum, and the risk for the mold formation is also very low. And then it also has improved thermal storage capacity and time lag effect. Therefore, it has better performance in storing heat and dissipating it inside of the building. It also has a U value that fits the passive house standard and has a significantly lower global warming potential compared to typical construction. Here is the detailed construction where the modules are interlocked with each other and joined with earth-based mortar. Here we can see that we also conduct a thermal bridge testing, and the result shows that our C value is very low compared to typical construction. This shows that this minimizes the risk for thermal leakage from the inside or outside of the wall itself. This will minimize the needs for additional energy for heating or cooling, especially during extreme climate conditions.
Here is the whole building testing for the daylighting and the thermal comfort, where for both scenario, the buildings show improvement, especially in daylighting. There's about 50% increase in natural daylight, and for the temperature, it falls within the comfort range of 21 until 25 degrees Celsius in both summer and winter. Here is for the new construction building, where we test in 2 different building typologies with different energy needs, and it also shows fulfillment to the standard.
We also calculated the global warming potentials and the embedded carbon using the life cycle assessment, where all buildings fulfill a tier A, which means it has very low carbon emissions. And the main carbon contributors are directed to the choice of materials and mechanism for the renewables, which means all the other things such as the transport, waste, and other things are very minimized due to its modularized design. The mechanism also fulfills 50% of building circularity, which means that half of the materials can be repurposed later. And we also did a whole system energy performance for the new building, and the results indicate over 50% of energy reduction from the baseline with heating and lighting demands, which are very, very low, demonstrating the system efficiency to temperate to cool climates. And here's how we implemented all of our strategies that can be seen from the building sections. Here's for the side A, and also the side B, new buildings in Villefontaine.
And here is for the whole building. That's all for our presentation. Thank you.
Thank you. Thank you, team number 5. Now, the last team in this session, we're going to call team number 6.
Hello, Taiwan. We are team number 6 from National Tsinghua University. Today, we are going to introduce the using trophanathan husks, coffee waste, and bamboo chopsticks as electro material to enhance the power output of microbial and plant microbial fuel cells. The global warming is a severe issue that, as a traditional energy, it produces lots of air pollution to damage the environment. So, what we try to solve is replacing traditional energy with green energies, since it has several positive effects on the environment. So, bioelectrochemical systems, microbial fuel cells, MFC, and plant microbial fuel cells, PMFCs. It converted the chemical energies into electrical energies. It has the advantages of environmental friendly and renewable resources and sustainable energies. However, it has the drawbacks of lower power output and high cost, leading to its limited applicabilities. So, our work is try to enhance the power output and also reduce the cost. So here's the question. How do plants and microbes to generate electricity? Well, for microbial fuel cells, first, when filtering the wastewater, the microbe will attach to the anode and interacting with the solution to produce the electron. The electron will transfer from the anode through the outer wire to the cathode to interact with the oxygen from the air to produce water and become fuel cells. Also, for plant microbial fuel cells, the nutrient will transfer from the leaves to the root and interacting with the microbes in the soil to produce the electron. So the electron will transfer from the anode through the outer wire to the cathode and also interacting with the oxygen from the air to produce water and become the fuel cells. So, if we coated our material onto the electrode surfaces, we can allow more microbes to attach to the electrode surface so that we can hire a higher porosity, surface area, biocompatibility, and eventually we can enhance the total power output. So, what's the innovation of our project? We use the 3 agricultural waste in Taiwan. First is trophanathan husk and coffee waste, and last but not least, the bamboo chopsticks. And through the chemical activations, we can obtain our final product, activated carbon. Despite from the advantages we just have mentioned above, the most important thing is they are low cost. So let's just look at the first 2 characteristics by the material characterization of SEM. By looking at the 3 images down below, we can see that our 3 material have a rougher surface area than the reference, CAC. This is our commercial activated carbon. so that we can say that our materials have higher surface area, porosity, and biocompatibility. So next, by looking at the XPS analysis, we find out that our three materials have increased oxygen-containing functional groups. This means that we can enhance the hydrophilicity in our material surfaces. This means that we can facilitate the electron transfer from the microbe to the electrode surfaces. And also, by lower degree of contact angle of our three materials than the CAC, we can also confirm this result. So next, let's look at the electrode performance as integrating the triple-Natanz Hart derived activated carbon into the NFCs. We have successfully enhanced the total power output up to the 1.7 times. And the next, we use the coffee waste as activated carbon into our PNFC. Eventually, we have success to enhance the power output up to 4 times. And last but not least, by integrating the bamboo chopsticks activated carbon into the PNFC, we have successfully enhanced the total power output up to the 3 times. And the most important thing is that we have reduced the total cost of our material down to just 1/5 of the CAC. And also our PNFC and NFC setup just meet the SDGs goal of number 7, number 8, number 11, 12, and 13. In application, we have successfully light up the LED and cottage. And also, we have cooperated with the TSMC to build a plant wall to light up the roof. So all we want to say is just light up the sustainable future with just a small bit of agricultural waste. Thank you.
Thank you very much, team number 6. Now, at this time, we're going to invite our judges all together come to the demonstration site to see their real demonstration. 我们现在邀请评审委员到我们前6组的展位进行他们的实际操作。
快到你那边了啊！好，你自己接。好，你自己接。好，不管你了，我就说。
Okay, first we have a timer over there. 给他们看一下那时间表。那个 iPad 可以往前，那边是计时板 timing， 所以你可以 for 6 minutes right there. Yeah, it's timing. So if you're okay, you can start. We're gonna start timing. Thank you. 等一下，提问。
Hello everyone, we are Team 1. So we are excited to explain our project, like how we transform waste to worth. So in the beginning, we use like carbon capture technique. Here we use like waste materials like cement slag, steel slag, waste brine, waste brine, seawater brine, and calcium oxide. Through a modified solar process, we get like sodium bicarbonate. This is like a carbon source for the microalgae.
And in the second stage, we have microalgae that is grown using captured carbon. And then the final harvested biomass is fed to flies or insects for us to extract refined oils in biorefinery process. So we have microalgae here, just like other plants, it needs light and carbon dioxide for growth. So after we capture the carbon from the first stage through the modified sulfate process, that one, and we feed that into the microalgae cultivation system. In this bottle, we also install some kind of gas plate to ensure a homogeneous dispersion throughout the whole cultivation system. And our highlight of this microalgae cultivation is we generate a new strain other than the natural strain. So here we have the natural strain that Chlorella sorokiniana, one kind of microalgae that is easily found in Taiwan. And the other one is edited using CRISPR technology. Then we found to have higher lipid production by up to 70%.
So from here we get like output is like a microalgae powder, and you can see this is a microalgae powder and some kind of like oil. So we feed this one
to the insect biorefinery. And you can check here. Yeah. Here you can see like insect biorefinery. Here we can like the metabolism of like different kinds of like insects and flies can like alter like viscosity, and then this can like enhance the thermal stability of the lubricant. And then here you can see like a different kinds of like lubricant oils. One is like fly oil, and the other one is like a worm oil. So and then we go to the like how we formulate the biolubricants. We add some kind of like functional additives to increase the lifespan of the lubricant. And then we send all the like, data sets to the AI agent.
Okay, by utilizing the photosynthesis of the microalgae, we use to create the data set for the AI. So the AI is combining from the microalgae, the additives and the oil, and then feed it to the AI and the first AI here has a role to predict the D and G Raman spectra, and then the other AI is to adjust the formulation and then to find the best combination of this formula until we got the biolubricant performance, the high performance.
Yeah, and from here, so how can we like make it use in like industries? So we tested our lubricants with like American standard, American Society for Testing and Materials. It's like a formal test. It's like benchmark test for our like to evaluate like some kind of like oils, greases, and lubricants. And here we use like we use our eco-friendly biolubricant along with the normal mineral oil lubricant. So our eco-friendly biolubricant is like 50% more efficient compared to the normal mineral oil lubricant. So there's like a breakthrough in like lubrication technology. So and we can get like a sustainable future. Thank you.
Zero.
Absolutely.
Any questions from judges? Yeah.
Okay. So did you do any cost evaluation?
Yeah. What? Cost evaluation about economic benefits.
Economic benefit?
Yes.
We just want to like recycle every waste on the planet. Yeah.
Probably you can calculate the footprint. How much footprint carbon dioxide reduced?
Actually, we haven't calculated carbon footprint for the whole process of these, but for the microalgae cultivation itself, 1 kilogram of microalgae can capture 1.7 gram CO2. So it's 1 to 1.7. So from this alone, we have the excess of 0.7 gram CO2, and we sincerely believe that that can equal to the rest of the process. Yeah, especially when we use waste to culture this one.
I know many people just focus on convert the biomaterial into the SAF, but you select to the biolubricant. But do you compare which is the best way?
Yeah, we compared with like you can see this. We compared with like automobile automobile like emissions, and we found that like it's like we can say around like 3% of CO2 worldwide. Yeah.
I would say the impact is global. Snuff is only very small portion of the energy usage, but lubricant you use daily in your car, in your everything you use. So it's the impact is global and more everywhere, every time.
For aviation, people no choice.
Yeah, it's regulation.
Other choice.
Yeah, but for biolubricants, it's naturally biocompatible for biomedical equipment and for the food processing equipment.
Okay, thank you for Q&A. Thank you，谢谢。各位评审委稍后发言时候呢，麦克风尽量朝你的嘴巴，因为我们有录音，所以说有使用麦克风。Alright, now we'll move to booth of team number 2. We have a timer over there for 6 minutes. Okay, you are ready?
Good morning, judges. I'm pleased to introduce our novel process of hybrid sustainable aviation fuel. Our team consists of aeronautics and also chemical engineers, and we specialize in green energy technology and also process integration. The environmental impact of transportation is a serious concern, especially for the aviation sector due to its reliance on fossil fuel. To solve this, sustainable aviation fuel has become a popular choice. It is a green fuel made from renewable sources and significantly cut the CO2 emission. In Taiwan alone, there are 3 major airlines companies which require 6.6 million tons of aviation fuel and also require 0.13 million tons of SAF blending annually. However, current SAF technologies have several challenges. First, limited feedstock availability, huge hydrogen demand, and also high operating costs. To overcome these challenges, our study combines liquids and also solid waste by following the 3E concept, which is environment, energy, and also economics. According to the Ministry of Environment, Taiwan produced 77,000 tons of waste cooking oil and also 12 million tons of plastic waste annually, which is hard to be processed. So, what if these waste could be transformed into the next generation of sustainable aviation fuel?
Okay, let me explain the technical content idea. Our process is developed using absolute plus simulation software and inspired by our team experiments. This process includes 6 eco-friendly zones and utilizes used cooking oil and waste plastics as our feedstock. First, in zone 1, used cooking oil reacts with methanol to produce fat, fatty acid methyl ester, and glycerol is a byproduct. And in zone 2, long-chain molecules undergo hydroprocessing with catalysts to cutting them into short-chain alkanes. In zone 3, waste plastics is heated without oxygen. To break it down, gases and liquids are separated and refined in the hydrogen-rich environment to produce PP SAF. Finally, the 2 substreams are pretreated and then combined to form our final product, hybrid SAF. Traditional process requires excess hydrogen, causing the big challenges, and their economic feasibility remains a big dilemma. In our novel design, in situ green hydrogen production units use byproducts such as glycerol and methanol from previous steps, providing enough hydrogen for our process. Unlike jet fuel and HEFA cases, our process needs less hydrogen. The excess hydrogen can be sold for additional revenue, making our system self-sufficient. The traditional process that produces jet fuel emits tremendous CO2. In contrast, our carbon emission data shows we reduce it by 91.6%. Now, please look at our poster. As you can see, our SAF process is better than traditional Jet A1 and meets the requirements of AST standards. Also, we save 91% of carbon tax since our feedstock comes from waste and we have low purchasing costs. In conclusion, our novel industrial design shows CO2 emission of 10 kg per hour, almost 80% lower than other technologies. We use different ways to produce hybrid SAF, reduces the external hydrogen sources, and we target the combined goal of net zero emission and net zero waste. Thank you.
All right, question from judges?
Thank you so much for your wonderful presentation, Mr. So in terms of performance, so you can reduce the CO2, but what about the performance of the...
As we have said in our presentation, our SAF is already better than the other jet fuels. We reduce the emissions by almost 50% compared to other green fuels, like other traditional market SAF, which are already available. Yeah.
So why, but in terms of performance, in terms of how much power you
so in terms of energy density, we can say that a traditional fuel requires around 63 to 65 megajoules of energy, per kg, and our SAF is already 72. So it's a bit higher than traditional SAF, but it's a bit it's lower than the traditional fossil fuel. We can say that.
This one is the question, the answer I was expecting, but then maybe we can use it for another application, maybe short flights, I don't know, different.
So actually the performance, as you can see here, this one is gas turbine combustor. So we burn our SAF in a gas turbine engine. So we mimic in a gas turbine and we tested the performance. As you can see, the flame is quite stable. We also compare with the traditional J1. So the flame, also the propulsion of the combustion is similar. That's it.
Okay, I got another question about usually fuels needs a lot of formulations and additives. Do you need anything to mix with the original fuels?
No, Professor. SAF is generally currently now being blended with fossil fuels because it's a bit expensive. But as of our SAF, we don't need any blending. Yeah. It's a pure homogeneous liquid.
Anyone else?
Any safety issue about your?
Definitely not, Professor. It's 100% safe. You can put your money on our SAF.
Yeah, because I think so far there's not any real practical validation yet, right?
So our SAF is completely validated. Like even our simulated process has been validated using reference data.
Okay.
So our SAF is completely validated. Yes.
Yeah, thank you for your presentation. My question is, are these data derived from simulation or the real test?
Yes, Professor. The data which we show, like the 12 kg of CO2 per hour, is already at an industrial scale. Like we have used the same flow rate for an industrial scale. Yeah.
Wait, so we do experiment?
Come up.
All right, thank you. Let's go to the third case. Okay, thank you. Please mind the timer.
Good morning, distinguished judges, and may I introduce our project and the demonstration to you. So, as we just presented in the presentation section, our project is about the construction of a smart mini-grid system. And inside of the smart mini-grid system, we have two most major components. The first one is the renewable energy system, what we choose solar panels here. And the second one, what is also our research focus in the project, is the effective energy storage system. And in our project, we choose the vanadium redox flow battery as the candidate because this kind of system has a quite long lifespan as well as a high efficiency. So now may I have your attention on the table, please? So here is our real product about the flow battery. So this one, it is a single cell, what we used for lab scale investigation. And inside of this little single cell, what is the most important key component is shown here. So this is the electrode, which we use graphite fuel. And inside of one single cell, we need two pieces of electrode. And this is the ion exchange membrane. So this membrane will annul the crossover of the reactive species, such as protein. And here is the disassembled species of the single cell. So from the outside to the inside, we have the isolation plant and the heating plant. So these pieces, we have two holes drawn on the top. If we need to heat up this whole battery, we can insert the heating rod into this little hole. And the temperature of the whole thing will be higher. And this one is a aluminum-coated current connector. So we can connect the external electrode rod on the two holes here, so we can connect the current. And for this one is also the key component. It is called the flow field, and the material is graphite plant. So here we can see that there is some pattern on the top of this flow field, and this one is used to allow the liquid electrolyte to flow through into the battery. So during our operation, what will occur is that we have the fluid medium, which contains the reactive species. It will go through this way, flow through inside of the battery, and flow out. So after we have investigated all the single components inside of the single cell, we can make it larger. And here we have a 50-watt design. What we can see is quite larger. And the active area for this one is 5 times 5, which is 25 times larger than the smaller one. And inside of the larger stack, we have 5 single cells, which means that one of these cells is equal to 51 of this single cell. And also, it's very similar. During the operation, we have the liquid fuel through this inlet and go through all these components until it's throughout. So here we have a demonstration about the application of the liquid fuel cell. As we can see that we have the renewable energy system. What we use is the solar panel and wind turbine here as a demonstration. And this renewable energy system will be connected into the stack. And here we use two liquid tanks to add the demonstration. All this liquid energy media will be stored inside of these two tanks. And this whole system could be connected to the community grid as well as the home grid. And so this is all of our demonstration about this project. We also have conducted a numerical simulation to prove the feasibility of this system during the home application. So this is all of our introduce. Thank you very much for listening, and we welcome for any question. Thank you.
Thank you. The Q&A time, please.
Yeah, thank you for your presentation. My question is, have you ever applied your VRFV to the microgrid system? Real application to the microgrid system. The title is development of a small mini grid system, but I never see that.
Yeah, thank you very much for your question. So we actually conduct this project inside of our campus, and we have set down some solar panels on the rooftop of our campus building. But due to the size limitation, we cannot put the real stuff here. So we only bring the 50 watt as a demonstration.
Yeah, you list quite good data, but my personal point of view, the space and the weight are two key factors in this kind of applications. Any comments on this?
Yeah, thank you so much. For our current design, this is just a very primary design. So for the weight, we only control it to around 1 ton currently. And this data is for the 5 kilowatt design. Yes, and in the future, so in the future, our currently research focus is how to make the whole thing more compact, so that the overall rate could be further lower down. Yes, thank you so much.
The space comparison, you occupy space.
Yes, so for the space comparison, currently the size is 1,200 millimeters times 1,100 millimeters around, and this whole thing could be settled down on the rooftop.
Yeah, thank you.
Yeah, thank you so much for your question.
Okay, now let's time this up. All right, thank you. Let's move on.
Okay, thank you very much.
Thank you. And then we come to the team number 4. So please, the timer over there. Please use the mic. Right. Next up.
Good morning, everyone. Our team is the colorful community. So welcome to our project demonstration. Our project is dealing with all type of the lithium-ion battery, the real spent battery. So in the traditional method, the most challenge part is the delamination. How can we recover the anode and cathode material inside the spent lithium battery? The traditional method, they use the high temperatures or the toxic organic solvent to delaminate, to recover the materials. However, in our project, we use the room temperature, completely non-toxic solution to delaminate and recover the materials. After separation, as we can see over here, is the valuable metal, the critical metal over here. And also we can recover the copper and aluminum foil and also the separator. So my team member will present the next part.
Okay, after the separation of the current collectors and the active material, we can now go to the recycling steps. And we decide a continuous flow hydrometallurgy recycling method to deal with the current bottleneck of the complex cathode chemistry in the market. So we can effectively separate the like iron, manganese, cobalt, nickel, and lithium from the collected spent lithium-ion batteries. In addition, we can also fabricate the ternary cathode materials through the co-precipitation method, and also the lithium iron phosphate batteries. And we also further scale up this process to deal with the larger scale of the spent lithium batteries. And after we account for the cost, the profit for recycling lithium batteries is estimated to be $378,000 US. In our process, we also can reduce the carbon dioxide emission by 41% because we do not have a high temperature roasting process in our work.
And that's all for our demonstration. Thank you for your attention.
Anyone?
Thank you for your presentation. I had a small question. As your presentation, your message is very good, but I'm concerned about the percentage of the material can be recovered. Can you comment about this?
Yeah, after we calculation by ICP data, mostly about 97% of material we can recover.
But for the traditional method, how many percentage? You say the traditional method maybe high energy, because the input they operate at high temperature.
For the traditional method or recovery of the materials would be around 98, 99.
Should be much higher.
Yeah. That's inevitable.
Okay, so in your presentation, you say it's a continuous process. Is it true? It looks like it's a batch process at this time. You mentioned it's a continuous process.
Yeah, so
now it looks like batch. So how do you compare the batch process to continuous?
Continuous process means following step-by-step recovery process.
So it's a stepwise process, not continuous process.
No, I mean our process is combined to critical process. The first one is the PVDF elimination process. So after we eliminate the active material from the copper or aluminum foil, then we can get this black mass, and we can just pour this in the tank, and it will continue to run to add the precipitant or the pH adjust solution, and we can step by step use the filtration to get this.
But still, that's for a chemical engineer, it's a batch-wise continuous, batch-wise unit operation. It's not continuous.
Sorry, I'm not a teacher. I'm a student also. First one, the feed can be continuous feeding, so it's a continuous process. And before they make the presentation, they said they are pre-treatment and after treatment. The pre-treatment means dismantle or threading, but in the future we will make integrate by the industrialized by automatic threading and delamination, the whole process. But actually, this process has been under installing by Cleanaway. But during the confidential agreement, we cannot release too much. Okay. However, the delamination process is a new invention. Thank you.
Right, the timers are over there, so please start.
Good morning, everyone. Today we would like to present the flux, the sustainable construction proposal that combines shearing layer construction and PCA block technology to reduce carbon emission for construction. The proposal is applied into scenario retrofit, and new construction, all of them located in rural France area. The first proposal is our shearing layer construction method. This method divides the building into separate layers with different lifespan, allowing each layer to evolve independently without interfering with the others. The structural layers act as a backbone of the whole system. It consists of CLT module structure that serve both as a structure and building envelopes. This space plane layer, which consists our PCB block construction, as an interior envelope and act as a thermal mass for passive fittings and minimizes heat loss. Furthermore, there was a stuff layer that consists of the elements that constructed the interior. Both inside the layers can be reconfigured over time without altering the structural frame. This modularity enables the building to adapt and changing spatial needs. The skin layer consists of a modular system such as sun space and shading devices. These components act as passive thermal buffers, storing heat in winter and reducing reliance on mechanical systems. Here are the application of the shearing layer for new construction. And here, in front of you, is the physical model of the application for a laboratory buildings. This construction is constructed by a modular system, where the form is optimized through multi-objective optimization to optimize solar catchment and daylight autonomy. Furthermore, the result is applied in the form of the modules for the structure layers. Main CLT structure consists of the two modules that have been optimized.
Okay, so our second product is PCB block, or well known as ram earth block. So we developed a prefabricated PCB block system by compressing the damp earth into modular block, and then we stack within a structural frame. Okay, so our research initially started with our experiment with organic binders such as rice husk ash. We can see the sample. After that, we made the three main samples using process pozzolan to be tested. And all of the temperature differences and thermal conductivity value results can be seen through these diagrams. And this is the comparison temperature difference for the three main samples. The result shows that a higher pozzolan content consistently improve insulation performance. And then among all compositions, the 10% pozzolan mix over the best balance of conductivity and thermal lag for the French temperature climate. We also made the real-life scale wall section to be investigated, its thermal transfer performance through the same method as the previous sample by Hobo data logger. This is the equipment. And then the result is the thermal difference around 27 degrees Celsius, where the indoor room is constant at 25 degrees Celsius, which fulfill the comfort standard all year round in rural France area. With all assembly combined, as you can see, it achieved a U value that meeting the passive house standard.
So here are the application for the construction for retrofit scenario. And here are the scenario for new construction for laboratory building. And here the construction of the new construction of dormitory building. With all the construction scenario proposal, they can achieve thermal comfort all year round. Furthermore, we got grade A for every design proposal for low carbon emission for construction. We also got more than 50% energy reduced from ASHRAE baseline standards due to the passive system and its material that reduce heating and cooling load. Here are the detailed graph all year round of energy consumption. In summary, the flux demonstrated how our proposal can enable buildings to adapt over time while significantly reducing environmental impact and resource consumption.
Okay, we have 1 minute for question.
How can this? It seems like this very good presentation and stand up. It seems this system was developed for a special occasion, France. What about Taiwan, where we don't have so much space, for example? Because then it becomes
So we actually already did some combinations. So if you can see here, the system is actually so if you can see right around here, so we actually modularized all of the building components into standard market sizes of 1.2 meters. So this is also means that we can also change the layers, the insulation layers, and the combination, and change it into Taiwan. For example, for France, because it has a cold to temperate climate, we make the walls or the structures to be very thick. But in Taiwan or other tropical countries, we can also make with the same principle and the same sizes to be more thinner and more suitable for the tropical context.
Yeah, thank you. Yeah, you show three kinds of combinations here. My question is there any other combination to provide greater performance?
So overall, this is the only, all of these three is the best composition that we got, because the previous one we have tested with organic binder using rice husk ash, and as we can see, it had low strength, and there is like several voids and cracks. So this is the best one.
All right, thank you. All right, judges, let's go around the corner. This way, please. Team number 6.
Hello judges, we are team number 6. Before we introduce our topic, would you like to have a coffee? Because after making the coffee, we can obtain the coffee waste. So we recycle this coffee waste, we can turn it into a activated carbon. And also we also recycle the bamboo chopsticks and the waste troponatan husks. And we turn these three materials into the activated carbon. So we coated this activated carbon material onto the electrode and integrated into the PFC setup to enhance the total power output. And as for NFC,
NFC can use microorganisms to convert chemical energy into electricity directly. And on our study, we use troponatan husk activated carbon coated on the electrode of NFC, which can promote more micro attachment and enhance our power density of NFC. And this is our demonstration. We connect 4 batteries in series, and the data are displayed on the screen. And the 4 little battery can generate approximately 4 volts, which indicates the potential of NFC in sustainable energy.
so also we have successfully light up an LED by PFC setup. So let's take my microphone to the hand answer.
Yes, and after you're drinking your coffee, and we collect all the coffee waste like this. Yes, and from this machine, and we will do the material synthesis, and then coating on our electrode, and then we also put in our PFFC systems, and we connect each other in series, and this also totally 24 parts. Yes, and it also can light up your LED. And let me show you.
ecosystem，这个是非常好的一个ecosystem。做很多的，要漂亮一点，做很多 ecosystem。
So how do PMC light up an LED? So when the leaves of the plant absorb the sunlight, it will produce a nutrient. We call it photosynthesis, and the nutrient will pass through from the leaves down to the root to become the exudate. That's what we call it. And the microbe in the soil will gather this material, or we say organic matter, and turn it into an electron and hydrogen and carbon dioxide. So if we put the anode into the soil, the microbe will attach to our electrode. So we coated our material onto the electrode. We can have a higher surface area, have a higher porosity, higher biocompatibility. So we can allow more microbe to attach to the electrode surfaces. So overall, we can enhance our PMC power output.
We can look at these Christmas trees. Yeah, and there's a LED for just powered by our PMFC system itself. And we don't use any superconductor or something. We just connect to each other and using this to control our LED. And it can light up for more than 40 LEDs. And that is damaged trees, and you can look at this. And it also can light up for over 12 hours. Yeah. And because this PMFC is also from photosynthesis, so it still a leaf, and it can generate power continually. So we just need to take care of our plants. Yes, and that is our presentation. Thank you.
Okay, now QA.
Yeah, my question is the output of this kind of fuel cell is quite low. You already demonstrated the application field, especially for decorative, the Christmas tree or something like that. But for real energy application, do you comment about this? The application domain for real energy system.
Oh yes. We want to have a combination for example, demonstrate for this light, and we also can combine with agriculture. For example, in the large-scale agriculture, it will light up for plants at night. Yes, beside the highway. Yes, if you have experience, yes. Yeah, and we also can combine. And we also can combine with the green building, green energy or agriculture, like a plant wall or plant roots. Yes, and if we can use it for the series and a lot of scale, it will move on and power a lot of sensors.
Also notice that water is necessary.
Yeah, because it is wet soil, and this wet soil also from Hsinchu.
So water as a medium is necessary.
Yes.
It's necessary for hydrogen to transfer from the anode to the cathode.
Alright, okay, now dear judges, we have 16 rotatingly completed demonstrations. 这样各位评审委员，我们现在有10分钟休息时间。
All right, now it's 36. We're going to call the team number 7 on stage for presentation. The time is counting by your first word, please.
Okay, good morning everyone. Here we are from the team 7. Here I would like to present about our topic, the toward carbon neutral energy storage, current modification of VRFB electrode via atmospheric pressure plasma jet deposited p-metallic oxide. In the recent years, to achieve the net zero goal, some countries in the world has transformed to use the renewable energy, including Taiwan. However, when we use the renewable energy, there is a problem where sometimes the energy production is very high and sometimes the energy production is very low. That's why here we propose to store the energy when the energy production is very high using the vanadium metal flow battery. Why we need to use the vanadium metal flow battery? Because it has long lifespan, it's around 20 years. And it's safety because the electrolyte is not flammable. And then because it only use one vanadium material, so it can be recycled. And then the next one is it can be scaled up for the higher capacity by just scaling up the electrolyte time. In the vanadium metal flow battery, carbon is widely used as the electrode material because it has high conductivity, large surface area, chemical stability, and cost effective. However, when we use carbon, there's some limitation that we need to solve the problem. What is the problem? One is carbon has poor electrolyte wettability, and it has the low surface activity, and it has poor catalytic performance. In the recent study, some researchers tried to enhance the performance of the electrode by depositing the metal oxide on the carbon material. However, the traditional method, they need several steps to deposit the metal. They need to prepare the metal oxide powder, and then they need to do the pre-treatment. So this is very complex, and it's consuming a lot of time. And another way is the process also produces a lot of the residue, this is not good for our environment. And this is also difficult for the mass production. That's why in this project, we propose to use the atmospheric pressure plasma jet to modify the electrode by depositing the p-metallic oxide. Why using the IPPJ? Because the IPPJ, this is the green method, where the process can have no any residue, and this is the good one for our environment. And then the IPPJ, it can operate from the atmospheric pressure, so it's possible to use for the mass production. And then the process is very fast and highly uniform deposition. And this is the setup for our system. We have two different setups. This is for the lab scale setup, and then the next one is the mass production setup, which is we already have the collaboration with a company for the mass production setup. And we will explain more in the demonstration session. And when we finish the deposition, the modification on the electrode material, then we will assembly to be in the single cells. And then this is the setup for the VRFB. This is the different result between the pristine on the commercial electrode and our modification electrode. You can see here, the commercial electrode is very hydrophobic. After we modify the electrode become hydrophilic. And we use the XPS spectra to confirm that our element is well deposited to the electrode. And then this is the electrochemical test. From the CV curve, we can see that the redox reaction is enhanced, and then from the EIS, the charge transfer resistance is also enhanced. And this is for the charge discharge performance. Yeah, we can see here, in overall, the performance is enhanced at least 4.5 times at a low current density. And at high current density, it enhances more compared to the commercial one. And then this is the efficiency performance. You can see here, we try to use some different current density. By increasing the current density, for the commercial electrode, the efficiency is degraded. And then at a very high current density, at 120, the commercial one cannot perform. And our modification one, it still perform the high efficiency around 75%. And we also try to use the stability it has quite stable around 80%. And why this study is important? You can see the difference between commercial and our modification. The energy efficiency is enhanced. And then from 2024 data, using the renewable energy data, assuming only 10% energy will be stored in our system, we can store more 53 terawatt more energy, and then we can save around 133 billion money per year. And then the contribution to the net zero emission, this is the data from the International Energy Agency. We can calculate that the commercial one, it can reduce the carbon emission around 300 million ton per year, but using our electrode is around 360 million per year, and the difference is around 52 million ton per year. And this is the conclusion.
All right.
And
Thank you.
Thank
again.
you.
Time's up. Thank you very much. All right. Thank you. And moving on to the next team, number 8.
Good morning, everyone. To all judges, my name is Christopher. I'm from University Malaya. Today, I'm going to share you about our new wind turbine technology called an integrated cross-axis augmented wind turbine. So, why wind turbine in the first place? As we all know, wind turbine is the most mature renewable technologies, which still has a large and growing market. In Taiwan itself, it is predicted to grow around 55 USD billions in 2031. And globally, it is predicted to grow until 550 billion USD in 2034. This shows a great opportunity to do a research and development, especially to solve the current problem of wind turbine industry. So what is the major problem of wind turbine? This is a horizontal axis wind turbine, as we all know, which is commercially used in the market. This has a mechanical and electrical components, and most of the significant components is located on top of the structure, causing it a very difficult to do maintenance, costly, and also it's very unsafe for the worker to do so. The horizontal axis wind turbine operate at a high tip speed ratio, which has a loud noise and also a risk of birds and bats. Although it has disadvantages, horizontal axis wind turbine still has the best efficiency in the market, reach around 0.5 maximum, and it's also able to self-start by its own. Compared to that, vertical axis wind turbine can solve the structural problem of horizontal axis wind turbine. However, it has a very low efficiency, only around 0.3 to 0.4, and it cannot do a self-starting. It needs a motor to help it to self-start. Because of that, our cross-axis wind turbine was designed to solve this problem, to able to have a comparable power coefficient or performance, and also it able to self-starting while maintaining all the equipment near the ground level. Let's dive deeper into our cross-axis wind turbine. So cross-axis wind turbine, it consists of two components. One is the blade, and the other one is the augmentation device. The blade consists of the vertical blades and also horizontal blades. And the augmentation device works as a flow concentrator to channel the oncoming wind towards the horizontal blades. This mechanism boosts the power performance to be comparable with horizontal axis wind turbine and also able to self-start. From the picture, you can see all the equipment is near the ground level. This provides a very stable system. It has a low center of gravity, and also it has a low overturning moment. This is a very crucial parameter in offshore development. It reduces the stress in the floating platform and also mooring system. This further lower down the cost for offshore installation. So what's our research at the current stage? We have a CFD simulation, and we also have a wind tunnel testing at the small-scale prototype. The wind tunnel test showed that we're able to start that this prototype able to self-start at 2.8 meter per second. It's also show a power coefficient improvement by 140% compared to conventional vertical axis wind turbine, and it matched the performance of horizontal axis of the same size. The wind tunnel validate our CFD result with around 2% error margin, which give us the confidence to design a larger scale, and we inspect it through CFD simulation, and it able to reach 0.5 power coefficient. We also have plans for field testing for further on the bigger size, bigger scale, supported by a grant, industrial grant with Petronas. So what's the potential application of our cross-axis wind turbine? First, we can install it in a high-rise building. As we all know, high-rise building has a very turbulent wind condition, which for cross-axis wind turbine, it is very beneficial, especially the vertical component by obstruction by others building. It can support the horizontal blade of cross-axis wind turbine. And we also can install this at offshore application because it has a lower cost in the floating platform and mooring lines. We can install it in green hydrogen production because it has it able to work operating in a low to high wind speed, and especially in a wind farm application. Our cross-axis wind turbine can be integrated to the current wind farms of the horizontal one to capture the lower wind speed condition at the lower height. This is so far our achievement for the cross-axis wind turbine. We have an international patent. We win an intellectual property awards. We have won a best design award. And we also have a very high and strong publication in a top 5% and top 10% journal. Thank you.
Thank you very much. Okay, well, moving on to the next team. The team number 9.
Hello. Hello and good morning. I'm Julissa, one of the co-founders and CFO of Element Trailer. At Element Trailer, we believe trailers shouldn't be passive dead weight. So we decided to re-engineer them into active, intelligent systems that are more efficient and much more sustainable. Towing is one of the most overlooked challenges in transportation. It can slash an EV or ICE vehicle's range by 30 to 50%. But the biggest challenge is emissions. Towing a trailer increases carbon dioxide, carbon monoxide, and nitrous oxide emissions across nearly all driving conditions. When you hitch a trailer, emissions automatically skyrocket. CO2 emissions rise by up to 60%, and pollutants like carbon monoxide and hydrocarbons can spike tenfold. But we estimate that if Element Trailer were adopted at scale, U.S. fleets could cut 7 million metric tons of CO2 every year. That's the equivalent of removing 1.5 million cars from the road. Towing is a hidden emission source that has been ignored in sustainability planning for far too long. But we're here to change that. As we know, towing weight significantly increases CO2 emissions across all vehicle types. For internal combustion vehicles, hauling just 500 pounds boosts emissions to 107% of the baseline. And at 1,500 pounds, it climbs to 120%. Even electrified powertrains aren't immune. Hybrids see emissions at around 118%. PHEVs are at about 120%, and full battery EVs reach 125% compared to their unloaded baseline. That's precisely where Element Trailer comes in, by reducing towing drag and capturing wasted energy right at the source. Our team began with the proof of concept, a remote-controlled model to validate our ability to capture and reuse energy during towing. And the data confirmed our hypothesis. That success led us to build a full-scale working prototype. Today, that system is not theoretical. It's real, engineered, and ready for commercial trials. Element Trailer isn't just an idea. It's proven hardware and ready for deployment. We've even begun speaking with potential customers that are willing to test and implement our product into their fleets. Now, let me walk you through Element Trailer's prototype and highlight its advanced engineering and autonomy features. At its core, we use a lithium iron phosphate battery paired with a motor, synchronized through mechanical couplings. This setup delivers efficient, high torque output tailored for towing loads. Our system also integrates regenerative braking synchronization, allowing the trailer to safely recover kinetic energy. We've also embedded a load cell directly into the hitch that translates forces into signals, and our control unit converts it into motor commands. It's a closed-loop, feedback-driven system that keeps the trailer dynamically aligned with the towing vehicle. On top of that, we've developed a semi-autonomous and remote control capabilities. From a remote interface, operators can manage or position the trailer, which is ideal for tight parking or setup scenarios. In addition, we are working with Professor John Liu's team to design the best lithium-ion batteries and battery control systems for Element Trailer. Professor John Liu is currently leading key federal programs for electric vehicles in the US. In short, it's not just a trailer, it's a smart, self-assistive system engineered for maximum performance, safety, and usability. At the heart of Element Trailer is our real-time closed-loop control architecture, essentially giving each trailer its own brain and powertrain. Multiple sensors measuring and feeding live data into the controller. The system processes this in milliseconds, dynamically allocating torque to keep the trailer seamlessly synchronized with the tow vehicle, while minimizing driver intervention and energy losses. Think of it as active trailer intelligence, not just passive cargo. Now, on the left, you see our trailer under remote control. Operated seamlessly by the user via our custom interface. Meanwhile, the right window shows real-time data. From load cells embedded in the hitch. This shows our system's ability to integrate remote, human inputs, and live sensor data, enabling semi-autonomous performance and truly intelligent towing experience. So, while trailers seem ordinary, they are a massive source of hidden emissions and inefficiency. But with Element Trailer, we can turn them into powerful tools for climate action. Let's tow smarter and go farther together.
Thank you. Thank you very much. Now we're moving on to the team number 10. Please be ready.
Good morning, judges and fellow participants. My name is Ulia from International Team Number 10, and today I'm going to present our idea regarding lithium from trash to treasure, integrated flow battery system for scrap battery upcycling and carbon dioxide to lithium carbonate conversion. This innovation actually solved two urgent problems: CO2 emission and battery waste into one circular, profitable solution. And here, the outline for today's presentation. I'll start with our motivation. The rapid rise of global CO2 emission will reach to 1,000 ppm by the 2100, and it primarily driven by the transportation sectors. In response, the world is shifting to the electric vehicle powered by the lithium-ion batteries as low-emission alternative. As we know that lithium is key active material, but it's scarce and non-renewable. Million tons of lithium-ion battery waste often landed up on the landfill, and some toxic metal often goes through the environment. These two bad things, two problems usually solved by disparate techniques. But one using recycling and the other one using carbon capture. But have you ever imagined that two bad things can be really useful for us, especially for generating an electricity? And interestingly, it can be happen in one device at the same time. But how? Here is our innovation. A novel design technology that simultaneously uses two major gases as sources, CO2 emission and also the spent lithium-ion battery. The CO2 gas from the industrial and also the transportation sector goes up to the atmosphere, and it will be captured by the organic material. One of the most known is neutral red, but you don't have to be worried because there's a lot of organic material alternative that can be used and having the same ability, but even in a lower price. Through the electrochemical processes, this organic material can capture the CO2 gas to form bicarbonate ion and hydrogen ion in aqueous medium. This hydroxide ion will continuously react with the CO2 gas to form carbonate ion, which is easy to react with the cations. In our system, it would be act as a catalyte. On the other side, we're having and collecting a lot of battery waste, and we discharge it until it reaches 0.25 volt, dismantle them and spread its component, and we collect the black mass. And we proceed the black mass with the acid treatment and some additional of sodium hydroxide to precipitate the metal, and we can collect the lithium hydroxide as lithium sources in our system. During the operation, the lithium will pass through the membrane and will react with the carbonate ion to form lithium carbonate. And the most important thing is it can be generating an electricity. The beauty of our concept is it provides two outputs. While it generating an electricity, the lithium will react with the bicarbonate ion and will forming either lithium bicarbonate or lithium carbonate. So in our system, we can selectively choose what kind of material that preferably form by maintaining its pH value. So we cap the pH above 8 to increase the CO2 efficiency and increase the lithium carbonate conversion. As we know that lithium carbonate is also useful for us, especially for new batteries material. And based on the research that published on the Nature Communication, the neutral red having the amine group on its structure and it having ability to capture the CO2 gas during reduction, this neutral red transformed to the leuconeutral red and releasing by hydroxide ion. And hydroxide ion will continuously react with the CO2 gas to form bicarbonate ion and will continuously reacting with our lithium sources to form either lithium bicarbonate or lithium carbonate. As I mentioned above, that we have to maintain the pH above 8 to more likely forming lithium carbonate in here. So in our result, we expect it to be forming lithium carbonate with high purity over 90%, and it achieving high energy over 50,000 milliampere hour per liter. And here is our experimental setup. As you can see here, we have the flow barrier system with a neutral red before and after reduction and lithium sources before and after reduction. This was proof our concept that carbon capture and also a lithium recovery can work in one device. Actually, our innovation have so many benefits, and it aligns with several United Nations Sustainable Development Goals, especially for SDGs number 3, 7, 9, 12, 13, and also 15. In conclusion, our system is different because it is integrated system, economical system, and also sustainable system. Because it is solving two major waste sources in one system, it is providing both electricity and also marketable material, and at the same time, it is avoiding high cost or energy and avoiding the high waste from the traditional recycling process. Lithium doesn't have to be traced, and CO2 doesn't have to be treated. With the right technology, we can transform them into clean energy future. This is not only a recycling process. This is deciding how we see the waste. Waste is only waste when we waste its potential. Together, we can turn the waste into power and the trash into treasure. Thank you for listening.
Thank you. Thank you very much for your presentation. Now, next we move on to the next team. Please be ready. The next team will be Team 11.
Good morning. We are Team 11 from National Taiwan University. Today, I want to brief our work, multifunctional water purification device. And first, I want to begin with a question. How important is water? Water is often mentioned together with air and sunlight because they are essential for life. Yet, unlike air or sunlight, no living thing on Earth can survive without it. And that is how important the water is, both to us and our planet. And because it is so essential, it can also destroy lives when contaminated. In the 2020s, water contamination claims more than 1 million lives each year, around 400,000 every day. You might be thinking, who caused all this suffering? And who is responsible for such misery? Of course, it's us, always has been. Since the Industrial Revolution, water contamination has been a global crisis. The point is, once wastewater enters nature, no one escapes its impact because every living thing needs water. The one thing that we should never forget is the relationship between us and environment. Human and environment are inseparable. If we care for it, it sustains us. But if we harm it, it harms us back. So that is also why over 1/3 of sustainable development goals involve environment. And clean water, of course, is among them. So, what is our team doing to fight against water pollution? We create a multifunctional water purification device that combines several key features. 1. Activate carbon for removing heavy metal ions. 2. Functional bacteria to accelerate the breakdown of organic pollutant. 3. Porous structure for faster, more efficient filtration. And 4, ceramic component to enhance strength and durability. The unique advantage of our design is that the device supports targeted pollutant removal by encapsulating specific bacteria in different modules. We can tailor each device to treat particular types of wastewater, improving pollutant breakdown efficiency. Moreover, these modules can be selected and combined based on the wastewater's specific pollutant mix, enabling optimized treatment while keeping operations simple and flexible. Just like going to the supermarket, put what you want into the basket. Easy as that. So in today's typical wastewater treatment process, our device can take the place of bulky, inefficient sludge systems. This not only cuts down on sludge production, but also greatly reduces overall equipment construction cost. Next, let's get into the core technology behind our design. Our device is made using a unique chemical vapor deposition process developed in our lab. Using an ice template, this method creates a porous scaffold that can encapsulate microorganisms or functional substances, giving the device multiple functions. The main material is perylene, a polymer known for its excellent biocompatibility and chemical resistance, ensuring the stability of the device. We have also conducted preliminary experiment to verify the feasibility of our device. We test our device by encapsulate adsorption materials and observe their ion adsorptions in iodine or gold ion solutions. We've also embedded bacteria within the porous materials, confirming its biocompatibility and support for microbial growth. In summary, we use innovative materials, eco-friendly manufacturing to produce a modular, multifunctional water purification device that optimizes the wastewater treatment and help fight against water pollution. Here's a list of the core technology-related patents that have been approved or currently in the planning stage. And finally, our team involved our advisor, Professor Chen Xianye, and 6 dedicated students. We hope this passionate effort will one day bring real impact, helping society and promoting environmental sustainability through our multifunctional water purification device. Thank you.
Thank you. Thank you, Team 11. Now, the last team of this session will be Team 12.
Good morning, judges and fellow innovators. We represent the Water and Energy Efficient Control Laboratory from National Chongqing University, Taiwan. Today, we present our project about the smart pressure control for desalinations, adaptive modeling, and wave energy boost for net zero water system. Next, let's begin with the facts. About 71% of the Earth's surface is covered with water, but only 2.5% are fresh water. And the rest of it is seawater, which cannot be used directly. Moreover, WHO says that 2.1 billion people lack of potable clean water, and this makes a global emergency in water crisis. These issues also tie in the Sustainable Development Goals, especially goals number 6, 7, 9, and 13, related to the water, energy, and climate action. The key solutions for this problem is desalinations using membrane process, especially reverse osmosis. Desalination using reverse osmosis proven more effective than the other membrane treatment. Reverse osmosis process take around 4 until 10 kilowatt-hour per cubic meter, which found then twice than the thermodynamic limits. It is give a potential for improvement. So how do we reduce that? We designed an integrated smart system that includes OWC, ACA, PLC, and also water pump that responds precisely to control input. In the system, water flow influences every part of the system. The PLC will receive signal from ACA, and also the PLC will receive energy input from OWC and adjust the pump operation accordingly. The next one is about our flow chart combining between 3 components of ACA, PLC, and also OWC. Our ACA modeling requires real-time information for the sensor as well as plan limitations, and then it will be calculated about the flux, recovery ratio, permeate flow rate, and the most important things is SEC, or specific energy consumptions. For our programmable logic control, it acts as the execution center, handling a real-time control task. It will communicate with a sensor, actuator, HMI, and also a MATLAB or Simulink where the SCA run in there. The PLC receives optimized commands from the SCA and then adjust the pump air valve operations accordingly. For the next one, about our OWC, it will generate a clean energy Gaussian wave. When the wave arises or falls, it will cause the turbine to spin, and we use bidirectional turbine in here. For the next one, let's talk about our result. We use a real plan data from a database to evaluate the impact of our system. The graph you see here is the comparisons between the pressure and energy consumptions before and after implementing our control. On the left, your left side, we can see that the feed pressures and SEC, this shows that unstable operations, which leads higher energy consumptions and less efficient of desalinations. On the right side, after applying our method, combining between ACA modeling with real-time PLC control, the pressure becomes more stable and SEC performance improves significantly. And we got the results. We achieved around 1 until 11% of energy saving with the final energy consumption range of 3.64 to 4.76 kilowatt hour per cubic meter. And the next one's about our PLC system supports the entire innovations. We use Modbus TCP protocol to establish communication between all components. The PLC will send and receive a data from the sensor and transfer it back into the MATLAB where the SCA algorithm process. And the HMI interface will allow us to monitor all the operations lively. Finally, the PLC will be responsible for controlling how energy from our wave generator is delivered to our desalination process. Now, let's take a look about our wave generations. First, we use wave data from the Central Weather Administration Taiwan, specifically in Penghu, based on the month of May, because we want to make it the system same with the real data. So in there, around 0.6 meter, but in our lift scale, we use 6 centimeters, and we got the results 0.0867. And about large scale, it's 10 times scale. We got 3.61 kilowatt hour per cubic meter with at least 75 until 99% of RO energy required are supplied. And in conclusions, first, our adaptive control algorithm acts as a productive intelligent layer, keeping the system stable, efficient, and also can achieve around 1 until 11% reductions of energy consumptions. And our Syncvatec, or wave energy system, can power 75 until 99% of the RO process. And the most important thing, our hybrid technology of our innovations is reduce carbon emissions by over 90%. Our project is more than just a technical solutions. It's a step forward about cleaner, smarter, and more sustainable future. With our breakthrough and your support, we can ensure that every drop of water and every watt of energy are truly matters. Let's make it happen together. If you are interested in collaborating with us, feel free to scan this QR code. We'd love to connect with you to collaborate and bring this innovation beyond the lab. Thank you for your attention.
Thank you. Thank you for your presentation. Now this is the second session for another 16. Now we are moving on to the demo site. The judges, please.
Okay, good morning, Professor. Here is the demonstration from our team. Please play the video. So we have two different setups for the APPG treatment for the electrode. One is for the lab scale setup, and the second one is for the mass production setup. We have collaborated with the company to set up on the mass production. And here we use the atomizer. From precursor, it will generate mist, and then from the mist, it will transfer to the APPG nozzle using the heat pipe. And then for the mass production setup, we have a conveyor, so we can do all-to-all production for the electrode modification. And then this is the result from the modification of our electrode. We have some different size. This is for the 5 times 5 centimeter, and this one is for 15 times 15 centimeter. And after the modification, we can see here. This one is for the commercial electrode. This one is very hydrophobic, which is not good for our VRFP. And this, please repeat again. Okay, you can come closer to see. Yeah, this one is very hydrophobic. Yeah. And then for the modification, it's become super hydrophilic, like this. Okay, when we finish the modification of the electrode, we do the setup for the single cell. This is the part of the single cell, and then this is the setup for the vanadium flow battery. And this whole process is only single step process. So the process is easy and very fast. And this is quite efficient from the mass production process. From the next slide. Okay, when we do the charge-discharge process, the electrolyte will change the color. But now we didn't do any charge-discharge. Okay, next. And then this is the software that we use for the testing, for the single cell testing. And then next. Yeah. We have done some different materials, not only carbon nickel oxide. We have done cobalt nickel oxide, and then we also have done the cobalt carbon nickel oxide. Using APPJ, we can use any material oxide to deposit on the GF. We just need to prepare the precursor, like this one. We can prepare with different material, with different elements. And you can see here, the efficiency is increasing when we use different, when we modify the electrode using different material. And we increase the number of the metal element, the efficiency is higher. And then this is for the stability. For the 3 metal oxide and then 2 metal oxide, it's quite stable for over 100 cycles. And for the 3 metal oxide, it's also stable after 300 cycles. Next. And then the next step, one of our advisors, Professor John Howard, we try to do the stacked single cell for the higher capacity of the PLIP. Okay, thank you.
Thanks for your presentation. I think the APPJ method is very good for the deposition. But the major problem is the how to make the uniform deposition for the large scale of the plant.
Thank you for the question. Would you go on the video again and play it again? This one is for the lab scale.
But the problem is how to...
Yeah, we have the movement table. So the nozzle will be moved with the constant speed. So this is to make sure that the deposition will be uniform. Yeah.
Okay.
So can it be measured? Sorry. So can the quality be measured?
Yeah, verify.
How to verify? I mean, the quality, you need to measure it.
We try to cut the electrode in the different part, like here, and we use SEM to confirm that the particle is well deposited on the GF at a different point.
It's a quite big
Yes.
material. So how can the material, the particle penetrate to? Is it uniform across, but uniform in the depth?
Okay, good question. So we do not only do the treatment for one surface. We will flip it and then we do the treatment for the both surface. Maybe it will deposit in the certain thickness, maybe at 1 or 2 millimeter. But this is good enough for the to enhance the vanity metal laboratory because we have a top and the bottom is well deposited the catalyst.
Okay, 30 seconds. Anyone else? What is one disadvantage of your technique?
Okay, as I present in the presentation, this process is only one-step process. So the process is very fast. And the second one is no NiCO2 for the process. This is also good for the environment. And because we use the air for the process, so the process is very cheap.
The only problem is that it's one step.
Sorry?
So the only disadvantage is that it's one step.
Oh, disadvantage. Disadvantage.
Oh,
okay. For the
you said yourself. Okay. Thank you very much. Now let's move on. Very clever. Yeah, you can just watch the timer.
Good morning again, once again. This is the cross-axis wind turbine as presented. So the cross-axis wind turbine consists of the blade part and also augmentation device. The blade part consists of the vertical blades and also horizontal blades. So the horizontal blades is actually come from the horizontal axis wind turbine that we orientated to vertical rotation, that it helps to boost the performance and also provide the self-start. If you can see from here, the augmentation device helps to concentrate the wind into a vertical component, so the horizontal blade that we turn orientation and harness the energy, the wind energy. So this is the wind tunnel testing that we did in a wind tunnel back in Malaysia. It shows that first we did experimental until 8 meters per second, and the most important thing that it helps to self-start, because vertical axis wind turbine usually cannot self-start by itself. So our wind turbine able to self-start at 2.8. This is the proof. We compare it with a vertical axis wind turbine. This is our cross-axis wind turbine. So the wind speed when it reaches 2.8, it's able to self-start. And as explained in the presentation, all the equipment is inside the augmentation device, so it's very safe in the future if we want to do maintenance. Yes. Yeah, wait, 2.8. So in the wind tunnel, we're able to self-start without any motor helps. And efficiency-wise, it's comparable to the horizontal axis wind turbine. Thank you. Any question?
Can you go back to the first video? Where you have this that one? Why the gas is going out? It's not going to the main driver, it's going outside so it actually seems like it's not starting.
Okay, so for this one, because we want this to be omnidirectional, so we try to test it at different orientation of the field. If we can see, this is we divide into 5 sections. The problem of this first prototype is, yeah, yeah, 60%. And this prototype, because it's 3D printed, the orientation is not accurate. Like there is a misalignment and stuff.
In your presentation, you mentioned this kind of system can be applied for the offshore wind farm. How large? I mean, how large the output for this kind of system?
Okay, so if we talking about the same power rated of the wind turbine, we will be able to produce either the same as the current horizontal axis wind turbine wind farm with a smaller area required.
But I know the horizontal system.
Yes.
Right now the maximum power output can be reached maybe 10 megawatt. But this kind of system, I wonder they can reach this kind of capacity. But in order for the offshore wind farm, the capacity should be bigger. It's more economic.
So in that part, we are trying to work with Petronas as the industrial grant to scale up this prototype. Because we also aiming for scalability until 1 megawatt per unit and stuff. So we can compare to the wind farm currently in the market. 1 megawatt, then become 10 megawatt.
1 megawatt for offshore.
No, I mean per unit, yeah. So we can install it in a wind farm, so it's very dense, yeah.
The key issue is the construction cost of offshore wind generator is very high. So if each unit of wind turbine, your design is very small, in serious, I mean, combine very many wind turbine, it still costs very high.
So we can scale it up to 1 megawatt, but it still need some time. We estimate need at least 5 years to scale it to 1 megawatt. Right now it's like we are reaching TIL7. So still smaller scale. But we also got plan to go in on offshore platform. Means for the wiring platform, for the small one, the smaller size, maybe 300 watt, 1 kilowatt. That one is for the pilot standalone wiring. Yeah. But for the compare with the offshore one, still need some time.
You got the patent in 2016. Yeah, my question is this concept mean approved for commercialization? Yeah, first question. Second question is, in Taiwan, there are typhoon. So for this kind of real application, how to stop or lock this wind turbine when the typhoon attacks this wind turbine? Thank you.
So for the patent, it's not commercialized. It's just an intellectual property patent for both this design we also filed the patent currently. For the locking in for the Typhoon, it will be still relying on mechanical or electrical brakes. Yeah. The benefit of that, we still like, because our equipment is down there, even if there is a brake or maintenance needed, it's not that hard to do.
In Taiwan, we have a Typhoon. Do you compare the two systems? Which one is the best, the good for the environment issue? Yeah.
All right, let's move on.
Thank you.
All right, this is team number 9 for the demo. Am I on camera here?
Start. Hello gentlemen, welcome to Element Trailer and welcome to our demo. This is our 1:10 scale model that we built. This was, we built it to solidify our claim of that we can increase range using our electrified smart trailers. And using this model, we were able to gain 3 seconds of range increase in this particular model. Going to the first prototype that we have built, we have started testing it with McNistry, one of the commercial fleet management companies in the US, McNistry Corporation, construction fleets. And there are some good insights from this testing. We were able to increase the range of the 2016 Honda CR. We tested with our 2016 Honda CR all-wheel drive, equipped with the all-wheel drive system, and we were able to increase the range by 16 to 18%. If I talk about some environmental aspects of it, we tracked the tailpipe emissions of the car. It was 156 grams of CO2 per kilometer. We cut it down to about 126 grams of CO2 per kilometer, giving us we saved about 24 grams of CO2 per kilometer. If projected annually, we save about 467 kilograms of CO2 per kilometer if we use systems like that.
This prototype is not just a concept. It's a working innovation in the field. And we already introduced the creative features for the multi-billion-dollar traditional trailer industry, such as motor synchronization, bidirectional charging, regenerative braking, and a modular interior adaptable to diverse cargo and operational needs.
Lastly, I'll be talking about the completeness of our work. So recently, we just finished demoing at McKinsey, one of the largest construction companies in the United States, with McKinsey strongly liking our product and encourages us to push further. We are also utility patent pending, which is not disclosed because it's provisional. We are currently in talks with potential investors from venture capitals all over the United States. So as you can see, the current state of our product is very convincing. Next up, this is our 1/10 scale proof of concept model. But here are videos of our full-scale prototype that we have developed being demonstrated and tested. So you can see that when we're controlling the motor in the front, it's synchronized as well. Now we're open to questions from the judges.
Yeah, thank you for your presentation. My question is there any communication in between for synchronization? What's the question? Second question is, any regeneration mechanism in your design? Thank you.
So I'm going to talk about our first prototype that we have built, not the model, but the prototype that we have back at home in the US. So we have a communication protocol. All of this is connected with Wi-Fi, and we are using some CAN bus controllers, automotive grade CAN bus controllers that we have to communicate all of the systems that we have on board. And for tracking the tailpipe emissions and other things, we are using an OBD2 sensors just to get the sensor data and correlate it what we have. Yes, so our trailer uses regenerative braking. Right now, we are able to use it. That's how we got the 16 to 18% of end range conversion in McNistry tests.
Okay, thank you.
Do you take into account about total energy consumption? Because in your presentation, you mentioned that the oil consumption with air resistance.
Yes.
So if you take into account total energy consumption, I think you will be better. Second question is regarding airflow resistance.
Yes.
Because the trailer, especially the shape design is also important.
That's a good question, and I like that you asked it. So I would like to share this with you. This is our concept sketches that how we're going to be designing the aerodynamic trailers at the future. So we are currently looking for investors to invest in us so that we can make that thing.
Yeah.
And thanks for asking that question. I really liked it.
So the answer is read it, and then you will know. So, but said what is the novelty? The novelty is the integration.
Yeah. So the novelty is that we have.
Because it's like a regenerative brake, all these is already existing. So your key is integration, I think.
Yeah. So thanks for asking that question. So I would like to point out what the key features that we have. That my colleague also told about that. We have motor synchronization, and all the control algorithms that we have built are proprietary to us, and they are being tested right now, and we are able to achieve, like I said, 16 to 18% of range increase in our gasoline-powered vehicles, and we hope that we'll be able to get at least about 30% of range increase in terms of if we try to towing this with an electric vehicle. That's what our hope is.
For the flat.
Actually, the test, as you can see in one of the videos, we used a track that has a gradability of about 30 degrees, and some.
But this is concept. In descent is harder.
Yes, descent is harder, but we used the hill. We used it in just uphill. So that's how we designed our track, and we also tested on gravel. So that's how our track was built around that.
Okay. All right. Time's up. Thank you very much.
Thank you so much.
I now move on to the team number 10. This is timer.
他的麦克风呢？
我先给他。
不行，你的系统不是这个系统。
Good morning, committee. Welcome to our group. We are from International Team Number 10, and our project mainly focuses on how to transform these waste batteries and CO2 gas from trash into a valuable lithium carbonate and also producing electricity. Here is our integrated system. In the catalyte side, we are having the reduced flow of neutral gas, Leopold neutral gas, that already reacted with the carbon dioxide gas to capture and have the bicarbonate ion. On the other side, we are having the lithium brine coming from the recycled electric vehicles batteries. Our experiment starting by this material, neutral gas. This neutral gas will be reduced with the presence of nicotinamide as the hydrotropic solubilizing agent in the potassium chloride solution. Here, we are using the anion exchange membrane to only allow the hydroxide ion movement from this side to the neutral gas side and having the Leoco neutral gas. Here, we can observe the color change and also pH change, and we also confirm the formation of Leoco neutral gas by using the UV spectrum. Here, the peak shift from 550 nanometer to 450 nanometer, and also proved by the NMR spectra that the NH bond is successfully generated by these two new peaks. Here, we are purging the carbon dioxide gas into the Leoco neutral gas solution to react and have the bicarbonate ion. The color will change from orange to red, back to that C, and prove the color change to prove the bicarbonate ion generation. This bicarbonate-rich solution will be used as our catalyte. Here, for the other chamber, we are having the lithium brine coming from the lithium recycling. Here is the vehicle scrap batteries from the electric vehicles company in Taiwan, and we will treat it with we will disassemble it and we will get the black mass. We will treat the black mass by using the hydrogen peroxide and also sulfuric acid, continued by the addition of sodium hydroxide to be able to collect this lithium brine, which is very rich of lithium hydroxide. This lithium hydroxide will be used as our supporting electrolyte in this chamber to transform the lithium to pass by the nephine exchange membrane to the catalyte site. On this catalyte site, the lithium will react with the bicarbonate ion to form either lithium carbonate or lithium bicarbonate that depend on pH. On our experiment, we carefully control the pH to be higher than 8 to make sure and increase the amount of lithium carbon dioxide generation. Here, we can collect the electrode and we will have the solid. Here, we will collect the solid and wash with the ethanol. Here, we will be able to collect the precipitate, which is containing almost pure lithium carbonate, as seen here. On the other hand, on the side of our membrane, it also having some precipitate, which also the lithium carbonate. But the key is, our battery is still able to run smoothly and maintain the voltage without any flow block, even though there are solid precipitate on the electrode and also on the membrane. We also connect our batteries with the LED light, and it can light up more than 1 hour that proves the concept of electricity generation. Our project is the proof that we can combine the carbon capture and also lithium recycle in the same device. And by using this device together, we can collaborate to achieve the net zero by 2050. Thank you.
Do you compare with the microphone? Okay. Do you compare with the other types of flow battery, like the VR and
So actually, in vanadium redox flow battery, we can't able to get this capacity, specific capacity. As you can see, the specific capacity is going 50,000 milliampere per liter. So if you see the other vanadium redox flow battery, it will go until like 300 or 500. But it is like we can recycle again and again. But here we are like acting as a primary battery.
So you mean that the output power is
yeah, it is very high.
It's much better than the
vanadium redox flow battery. And if you are like seeing the voltage will be near 1.23 volt because we are using aqueous medium. So if you go beyond that in vanadium redox flow battery, we can't able to achieve the voltage. But here we are getting the voltage of around 1.75 volt in aqueous medium. So we are using aqueous medium to produce 1.5 volt, and we are using recycled lithium ion battery. So it is like the cost is very much less and it is very much environment friendly, and we are comparing, it is a novel technique, like you can't able to see this kind of design on paper before because of the flow block. But we are not having any flow block, and we can able to see the lithium carbonate formation like clearly on the carbon felt and membrane, and we prove that with NMR also, lithium NMR.
How about the lifetime? What lifetime or the other issues and safety?
Yeah, it is.
The lifetime and safety.
So lifetime is like, yeah, actually we are not like vanadium redox flow battery. It is very new technology, but we are trying to prove. So until now, for like 2 days, it's been
the testing is ongoing.
Yeah, yes, Professor. And we found that like lithium carbonate can form at minus 2.2 volt. So like CO2 conversion. This also we can see as a CO2 conversion to a carbonate formation. So we found that the lithium carbonate can form on minus 2.2 volt. So that is also like unknown. We found that.
Okay.
Yeah.
I think the time is up.
Okay.
We are over time.
Thank you so much.
Thank you. This will be happy side.
good morning. Welcome to our group. We are from Team International 11, and in here we made a multifunctional porous water purification device. And before further explanation, we would like to start our demonstration first because it will take some time, and you can see the results later in several minutes. So in here we have our iron gold liquid solution as our wastewater sample, and then we will insert our device into it, and we can see that it will turn into clear water after several minutes. Okay, so for So our device is made with a technology called chemical vapor deposition, and this technology, along with the biocompatible material, which is paraline, we can make a 3D functional porous structure like this, and with this. And with this structure, we can encapsulate like several functional materials according to what our wastewater target. So for example, here in our sample, because we want to target the iron gold solution, so we use like a chylocene and glutaraldehyde as our absorption material. So in here, we have like our we have done this before in our lab. So here are the results. This is the before solutions, and after we have put in our device inside, you can see we can get like a clear water here. And not only that, our technology also allows us to make our samples, our device in several shapes. For example, here we have it in film shapes, and here we have it in cylinder shapes. So we can also custom it based on our wastewater. And if, for example, we have like organic wastewater, we can also encapsulate like specific bacteria and also enzyme inducers to break down the organic pollution. So we have done this before in our experiment, and we can show that we can have like a lower COD number after several hours. And also because the bacteria is being encapsulated in our structure, it is being protected from the harsh environment, and therefore we can get a good viability of the bacteria. And in conclusion, we made a device with a biocompatible material, which is paraline. And then we also, what makes our device special is that we can custom our device based on the wastewater pollutants. And based on our experimental results, we can get a high efficiency treatment. And last but not least, we use a technology called chemical vapor depositions that is 100% solvent-free and also have a 100% conversion efficiency. Thank you. So as you can see here, actually, the color is getting clearer compared to before. So is there any questions?
Okay. Regarding the application, can you utilize your technology to purify the industrial wastewater?
Yeah. Actually, because we can custom our device, any wastewater we can target it, because we can just choose like the absorption material or the right bacteria to degrade the pollutants.
Can the material be reused or recycled?
Sadly, no. So, because I think our specialty is that we can encapsulate like several things together and make the efficiency of the degradation higher. So we kind of focus on that part, but yeah, we still can use.
I have two questions. One is the stress. You already mentioned you use the thermometer to enhance the stress, the more, right? You're going to use the more, right? And how can you say something about the increase the stress. And the other is your process is very complex. You use the CVD to deposit some layer inside the mold. You will use the mold cross structure and how to make the very good composition inside the structure. Do you understand my question?
I will try to So because with our CVDs, we can actually make it in quite fast. I think like 2 hours can make our sample done.
Because you are the structure is the core structure.
Yeah.
How to use the CVD the deposit very uniform, very good inside.
Because here we use technology which is the ice template. So before we can input our functional material and it like a liquid, and then we will froze it, and then we'll act as our sample in the system.
Okay. Thank you. Thank you.
Welcome to International Team 12, and here is our display to present our ideas. Firstly, we have the innovation from RO controller. So we use the adaptive control in the MATLAB and Simulink and integrate it with the PLC as executor. And in the SCA, we can calculate and also detect the feed pressure optimal and also the recovery ratio based on the current condition in the reverse osmosis process. And then we'll transfer the optimal feed pressure and also recovery ratio value into PLC programming. So the PLC will be go to the VFD and then control the valve and also the feed water valve. And this SCA is benefit to be a double layer protection in the reverse osmosis process. So the system will be run within the plant limitation, so it will be not cement the membrane as well as the another equipment. And when the sensor has a value or error detection, the reverse osmosis process still operate within the safe condition, safe operation value. And this is the display for wave energy process. So we use the wave energy process to cover the energy requirement in the reverse osmosis. So in here we innovate that we use bidirectional turbine. So the wave will be go to the turbine moving, and then also the turbine when the wave goes down, it also the turbine still run. So it has its direct bidirectional of wave energy. And my friend will be demonstrate how it will be run.
Thank you. Just shortly, this part you can see it here. This part is book first, but we use as sensors in here in this demonstration because we cannot bring the sensor directly. So we use this part. We can adjust directly for the voltage. In here you can see also in this part voltage line. You can see that it will be changed directly. So it will be connected between that. But for this one is indicator about the backward and forward. About forward is calculations based on ACA. If the forward, it means that the water need the supply of pressure need more, so need forward. But if need a bit more or too high, it will be less use backward system. And about the water pump and also the pump, it will be controlled also by the ACA. And about this one, the turbine bidirectional, we actually collaborate with another university, and this one about the lab scale, because the weather transmission in Taiwan, we use Congo data is 0.6 meter, and we just use 10 times 6 centimeters of it. So this one, the combination between the OWC and our Sympatex. This is our Sympatex, and this is how it works. When we rise, it will be turn on the turbine, and then also when the wave is cool down, also will turn on the turbine. Because we use the basic direction. So
So your title is about smart control. So how do you make it smart in any simulated conditions? Pressure waves.
about the smart pressure control, we use for this part ACA combined with the PLC. Because before, without our ACA, in the company use only PLC to control, and then just for example, I want the pressure become maybe like 10 or 20, but it can directly use to, it will limit the macro lifetime. So that's why we use our simulations in ACA to predict, but we directly control with the PLC. So we try to connect a simulation into the case data, and it's already verified in one of the companies.
So it's about like the waves, about the waves of the ocean. If it has
actually, it has two innovations. The first about the RO process with the ACA, and the other one about to recover the RO process. Yeah, it's different. It needs to recover the energy of the RO because RO have a high energy. For wave energy, we still have the simulations in lab scale. Yes, but for our ACA, RO process already tested in the one of company in Taiwan. And we got patent in Taiwan for the Taiwan and USA about the simulations and of course about the regulatory for our ACA. Yes.
So it's your core technology ACA, right? So you
Yes.
have to try to improve that, but
Yes.
basically your core technology is
Yes, correct.
My time almost up. So 1 second. All right. Okay, thank you.
All right, ladies and gentlemen, we will start our international competition of the afternoon session. Now I invite team number 13 come up to stage to have your presentation, please.
Okay, good afternoon, and hope you have a great time during the lunch. And I'm Chen Jiaqian from INTL 13 at National Central University, under Professor Hong Weishen's lab. Okay, so it's an honor to be here and share our achievement with you all. So first, we kick off our laser processing through laser processing since 2019 to pinpoint the best performing high entropy alloys. And then we turned this winning formula into scalable fabrications and awarded the ROC patent in 2021 and 2023, proving its strong potential for industrial application. So now, let's dive into the exciting progress we've made so far. So what is the focus of our lab? Our lab focuses on the high entropy catalyst in seawater electrolysis for hydrogen production. And also, we're doing the scale-up and large area coating, and then integrating into an ion exchange membrane water electrolyzer, which is the AEMW system. And with this integration, you can produce a material with multi-element and exceptional long-term stability and durability. also to achieve carbon neutrality by 2050 and the mass energy need in industries like TSMC and the base load power limitation in Taiwan, we have to find a new solution that is renewable energy. Where renewable energy holds its great promise, the mismatch of the energy production from wind and solar make the energy storage super essential. And Taiwan, with abundant seawater resources and the base loaded power limitation, seawater electrolysis can help us turn the surplus power into a clean and a reliable hydrogen carrier to save energy. However, one of the biggest challenges of seawater electrolysis is the corrosion issue. And here, we figure out that the high entropy alloy might be a potential solution to deal with this problem. And actually, the concept of high entropy alloy is originated from Taiwan. And when it comes with the high entropy alloy, you may probably heard of Professor Ye Junwei, the father of high entropy materials from National Tsinghua University. And he proposed the concept of high entropy alloy materials in 2004. Since then, the field has exploded and over 5,000 papers have been published. And these materials are incredibly tough with high strength, wear resistance, and even in harsh environment like seawater. But here's the catch, that conventional bulk materials have their limitation, like a low surface area and uneven composition. So what if we want to apply the high entropy alloys in catalyst application? That's why we're going nano, to boost the higher surface area and even composition of material. And back in 1959, Richard Feynman said that there's plenty of room at the bottom, reminding us that the smallest scale hold the biggest potential, but every innovation meets their challenges, like how can we put multiple elements in a particle of 100 nanometer? And how to design the actual fraction of different elements. And is the material homogeneous or not? Sounds challenging, right? But don't worry, our lab has already cracked a code in our lab.
Starting the laser beam quickly heating the substrate. Use the
high
laser
entropy
flash
alloys
heating.
are challenging,
Direct
but their
synthesis
potential
of
is
high
huge.
entropy
And here,
nanoparticles.
we use the non-equilibrium laser process, start with quick heat, stable hold, and rapid cooling with only 1 second to form a uniform and stable high entropy alloy. And except for the laser method, we're also working on the hydrogen-oxygen flame process. And today, I want to introduce you a well-established hydrothermal method that can help us precisely control the particle size and morphology to help us scale up our high entropy catalyst. And also, we have integrated many catalysts in the electrolysis system cooperated with the Tripod Nano company. And for most conventional material, go with the spin-nail oxide. And but we went further. After adding the magnets, the phase changes into the hexagonal carbonate structure to help us build up our high entropy carbonate catalyst. Now we name it as HECC, the material with multi-element and also the exceptional long-term stability and durability. And in one single batch, we can produce 6 grams of catalyst, which is equivalent to the capacity of 3.6 kilowatts in water electrolyzer. And move on to the radar chart. We also compare our HECC with other middle entropy materials and also a benchmark noble metal RuO2 material. But still, we can see that our HECC show the best performance, both in seawater or without seawater condition. And furthermore, we also do the long-term stability testing over 1,000 hours with a decay rate at only 0.7%. And also, there's no chloride ion generated during the reaction. And the down part is a comparison between our HECC and the commercial material. And still, we can see that our HECC is the green one, shows the best energy efficiency, achieving nearly 90%. So in summary of our HECC, it has the high corrosion resistance that can be applied in the seawater electrolysis and also can achieve for industrial grade. And last, we successfully integrated our extraordinary high entropy catalyst in the large-scale MEA membrane of 15 by 20 centimeters square in AEMW system. And for the grand final, I just put a conclusion there that our HECC is ready for commercialization. And also, in cooperation with the Tripod Nano company, we also built up our hydrogen demo lab for integrated seawater hydrogen production. So thanks again for being here to share our journey with you.
Thank you for your presentation. All right, we're moving on to the next team. Team number 14, please.
Good afternoon, everyone. We are INTL 14, and I'm team leader Dochen Lin, and our teacher is Dr. Huang Chaowei. Our topic is green butadiene, a breakthrough in bioethanol conversion technology. Do you know that tires can be made from ethanol? The tire's raw material is butadiene. It can be made by ethanol. The major process is in World War II. But now, steam cracking is the main process. Due to the economical reason, the feedstock of steam cracking feedstock of steam cracking shift from naphtha to ethane. So the butadiene to ethylene ratio is decreasing. At the same time, bioethanol supply is at industrial scale. So from ethanol to butadiene is a promising process. Bioethanol to butadiene is a catalytic conversion. And it also can reduce carbon dioxide emissions by 51%. Because steam cracking both need very high temperature and very low temperature, it will waste a lot of fuels and energy. Ethanol to butadiene need bifunctional catalyst. Only use basic, only the acetaldehyde, and only acid, only the ethylene and diethyl ether. But we use basic and acid, we will get the butadiene. The butadiene, ethanol to butadiene consensus way is the Kagan pathway. First, ethanol do dehydrogenation to acetaldehyde, and then do aldol condensation, dehydration, MPV reaction, and dehydration again. Finally, we get the butadiene. But now, all the literature are all insufficient selectivity. The capital expense is still high because the butadiene selectivity is all around 60, and the yield still insufficient. It cannot be profitable. So we want to adjust the microstructure of the catalyst. We grow the MOF UIO66 with the dealuminated beta, and we add some zinc into the catalyst to induce the oxygen vacancies. Here's our synthesis part. Dealuminated beta and MOF precursors with the DNF, and we use autoclave to heat 2 days at 110 Celsius degree. After washing and dry, obtain butane. And then we add the zinc precursors and dry. Finally, we do pyrolysis and calcination. The powder from black to white, and we obtain the butane and zinc 0.8. Here's our catalytic testing equipment. Nitrogen and ethanol mixing in the vaporizer. And the vaporizer is 100 Celsius degree. And then we introduce into the reactor. The reactor is 350 Celsius degree. Finally, we get the product. And we analyze the product by GCFID. Here's our catalyst performance. Our ethanol conversion is 93.9%, and the butadiene selectivity is 65.5%. Comparing to other literature, we think our catalyst is competitive. Here's our references. Thanks for your attention. We are INTL 14.
Thank you. Thank you for the presentation. All right, next team comes to number 15. Please be ready.
Okay. Hello, everyone. Let me introduce our team. We are from Russia, Lomonosov Moscow State University. And our team, you look on the site. But thank you for your attention.
Yeah, so our project name is Backwind Rider. Actually we're here at a Net Zero Tech competition. It means that we're here pro-green technology, so no fossil fuels. So what can we use instead of fossil fuels? Actually wind, right? We want to build wind-powered vehicles so that they would only move because of the energy of the wind. So there are many projects that consider this problem. For example, Blackbird, they can move downwind 2.7 times faster than the wind, but they can't move against the wind. They can't perform upwind motion. So in 2015, our laboratory developed a new vehicle that can move against the wind just using energy of the wind. And it doesn't need any engines or accumulators, anything like that. How cool is that, right? We want just to, but this vehicle can't move in downwind motion. So we want to combine these two ideas in a single car so that our wind car will move against the wind and in downwind motion faster than the wind by just simply changing the gear ratio, so no complex redesigns. How we managed to do that? Of course, using mechanics. We built some mathematical models using aerodynamics that was proven effective for some previous projects of our laboratory. Here are some formulas, here are some numerical calculations, and numerical results show that our simulations actually show 10% better downwind speed than Blackbird. And Blackbird, it can't really move against the wind, but our car can move as against the wind and in downwind motion. So when we choose high gear ratio, we get upwind motion. When we get low gear ratio in some optimized value, we get downwind faster than the wind. So here are some prototypes. Here's a prototype for upwind motion. You can see it like this. And here is another prototype. It's downwind prototype. So you can see that they are actually the same. Only the gear is different from each other. Yeah, so actually how can we prove that it moves downwind faster than the wind? It's a really complex thing to show because it really requires some complex laboratory environment. But what we can really do here is we managed to show it using treadmill. So here on the treadmill, you can see that the treadmill moves to the left and the car goes to the right. How does it work really? The treadmill actually make car wheels rotate, and the rotation transmits through the gear to the propeller, and a propeller creates a wind flow. And because of this wind flow, we move in the opposite direction. But if it will only move with the speed of the wind, it would only stay in the same place relative to the treadmill. But we can see that it really moves in the opposite direction. So so that means that it actually goes faster than the wind. So where to use this? Well, actually any sorts of environments where there is some gas flow, wind flow. For example, we can inspect gas pipes in things using vehicles like this. We can actually put this vehicle inside of gas pipes, put some sensors on it, and inspect some conditions of the pipes. And it will move only because of the energy of the flow. It doesn't need any batteries inside. And the last but not least, actually this wind body is just a wind car, like a STEM toy. So it also doesn't need any batteries. And if you blow on the propeller, actually, it will move towards you, not against you. And this is something counterintuitive. And that's why it's really fun for children and for their parents. And it is really educational. And we think it can really get children interested in, in green technologies, in mechanics, and really by making them interested in this, we can make them interested in developing green technologies and actually building a better future for next generations to come, for all humanity. So, thank you for your attention. It was nice to make this presentation for you, and we'll be pleased to answer your questions at the practical stand.
Thank you, Russian team. All right, we move on to the last team of the third session, team number 16.
Hello everyone, we are team INTL 16. We are from the Department of Biomedical Engineering in National Taiwan University, and our advisor is Professor Zonghong Lin. So today we will present our project entitled Self-Powered Peptide Sensor for EE2 Detection, a sustainable platform for water quality monitoring. So what is the problem that we are trying to solve? First, we can see the outline of our presentation. And the problem that we are trying to solve is water pollution, because as we industrialize more, it would be natural for us to generate a lot of waste. And unfortunately, in this stage of time, a lot of this waste actually ends up in our water streams, which is, of course, dangerous not just for us, but also for marine life. And so this is a very important problem to tackle, which is why Taiwan has a lot of laws in order to protect its waters, and also, of course, almost all countries in the world have similar laws. So the contaminant that we are trying to detect in our waters is called EE2, which is an organic pollutant that usually comes from birth control pills. And it has been shown to cause reproductive damage in fish and also cause ecosystem imbalance and long-term public health risks. So actually, as you can see from the chart in the top left is the level of EE2 in water, and already some countries have unsafe levels of EE2 in its waters. And so measuring the amount of EE2 in water fast and also accurately is a very important challenge. So we are trying to solve this by using a triboelectric nanosensor as an alternative platform to overcome these issues. So let's explain what is a triboelectric nanosensor. So a triboelectric nanosensor is a type of sensor that uses the triboelectric effect, which is an effect that happens when two materials contact each other. Charges flow from one material to another based on its position in something called the triboelectric series. It's actually the same phenomenon that can cause electrocution if you touch a metallic object, if you have been sitting on a wool surface, for example. So we have used this phenomenon in order to create this microfluidic nanosensor in which water can flow in a PDMS channel that also can be, has an electrode that can be functionalized with gold nanoparticles and a peptide that we will show later to detect EE2. So this is our sensor design and fabrication. We make a mold first and then put PDMS in it, and then take that PDMS and the PDMS channel. And also we have a surface that we can put our electrode on, functionalize it, and then close our sensor. So this is the working principle of our sensor. And as you can see, when a water droplet flows over the PDMS surface and the electrode, it causes different charges to form on it. Now, the crucial point is that we need the amount of charges on this electrode to change based on the amount of EE2 that's present in the water droplet, and that's why we use this synthetic peptide, which after functionalizing the electrode with gold nanoparticles, this peptide can bind to these gold nanoparticles, and it has another end that can also bind to EE2. And so this actually changes the amount of, when water flows on it, if it has EE2, it will bind to this peptide, and it will change the amount of charges that are induced on the electrode. And this, of course, will cause a different amount of voltage to be measured by our sensor, which we can then correlate to the amount of EE2 in the water droplet. And so this is our peptide, which we have designed in order to bind to EE2 and to gold nanoparticles. And this is the molecular docking test that we did in order to see if our peptide can bind well to EE2, and we can see that it has a very strong binding energy of negative 6.73 kilocalorie per mole. And so we have then fabricated this device and tested it. And as we can see, we have the voltage output of our sensor can increase with the flow rate. So this is an event of just one water droplet passing on our sensor. And the channel length, the channel width also increases the voltage output. And also, with or without adding the surface modification that we talked about, changes the amount of voltage that we get out of our sensor. And so this is a cost analysis of our sensor. And as we can see, our system is very cost effective compared to a traditional prototype stage. Thank you.
Thank you. Thank you very much. Thank you, please. Okay, this session have only 4 teams do the presentation, so we move on to the demo site, please. Okay, this way. Yes, this way. You're right. I confused.
Hello, we are Team 13, and it's my great honor to share our technology about this today. And our lab, our team has engaged in the high entropy materials and hydrogen production area for several years. Today, this topic is we use the high entropy as a catalyst and use it in the seawater hydrogen productions. This technology can combine with the renewable energy and green energy, and also can resolve some problems like the solar power or the wind power, because this kind of power also work in a very short time and make a green energy. So they will have a pressure on the electrical grid. But according to this, we can change the energy into the hydrogen as soon as possible. Another is that during the reactions, we may have an ion selective problem, and another is the corrosion problem. We can see about that. This is also the normal substrate like the radiate and the narrow icon forms. And in real seawater, they just 15 minutes, you can see that they corrosion very hot. But all about this problem is not a problem in our lab because we use the high entropy material as a catalyst. You can see this. We coating on it. Benefiting from four major effects of a high entropy, we can produce the good performance and long lifespan catalyst. But another interesting is how we produce this high entropy catalyst in a nanoscale. About this, my colleague Yu will introduce our special technology in our lab.
I'm Hong Yu, and now I will introduce how we to do high entropy material. And basically here, we put the precursor on the GDL and use laser power, and the catalyst will burn on the substrate. And the interesting thing is the laser spot can quickly heat into 2000 K and cool down to room temperature. We need 1 second. And the fast heating up and cooling down process is helped to from stabilize phases. And as we applied 2 patterns for this technology. And based on this idea, we also developed an oxide hydrogen flame process, and it currently achieved large area coating of 30 by 30 centimeters square. Okay, and next, my colleague Yunlin will introduce more information.
Hello, I'm Yunlin. Next, I'm going to show you our integrated system and our achievement. Besides laser and oxy-hydrogen flame treatment, we also mass production our high entropy catalyst in powder form. Because some of company request powder to use their own coat spray technology to coat catalyst on substrate or membrane. Yes. So with catalyst production, it's easy to scale up. We also develop large areas water electrolyzer system to water electrolysis. Okay. So here we can see this. We also completed technology transfer with Tripod Nanotech and also established a hydrogen demonstration site at NCU. And what's more, our lab also have collaboration with a lot of companies such as Wistron Corporation in Taiwan, Brembo Energy from the UK, and the Stanford University. Through this international and industry partnership, we can rapidly enhancing our capability. And last, in conclusion, we help to accelerate the hydrogen economy in Taiwan. Okay, thank you again for your listening. Thanks.
Okay, thank you for your presentation. Yeah, since heating up to 2000 K is required in the presentation, my question is, what is the cost or energy or footprint for your work? Thank you.
In this machine, we use 50 watt just in a very small area, so we can produce this very high. And it costs, we have calculated 1 centimeters, and it costs maybe 2.5 to 3 NT dollars per our catalyst per 1 centimeters.
As you just mentioned that your lab studied this topic for many years.
Yes.
So what difference or improvement you have done this year?
Okay, last year we also doing this again, but we use the pulse laser, and in this time we have another new system. We call it HECC, high entropy high entropy carbonate catalyst, and we use the hydrothermal waste. And because we have said that in this we just coating in situ growing on our substrate, and this new technology we produce the powder, so it is more useful.
How do you? Thank you. Very nice. How do you measure uniformity distribution?
About this we have
is the accuracy.
Do the SRF and the TEM index mapping, we can see that from the scale of the nanometer, we in 20 nanometer is very uniform, so we make sure that it's a uniform high entropy material.
Is it enough?
And also we do the SRD pattern, we can see that it's very beautiful spinel structures. So we make sure that it is good high entropy materials. This is my answer.
Good. Thank you.
Okay, thank you. Time's up. Thank you.
Thank you.
Perfect control. All right, we move on to the next team 14 for the demonstration.
Good afternoon, everyone. We are adjusting the catalyst of ethanol to butadiene. Ethanol to butadiene can reduce carbon dioxide emissions by 51%. And we adjust the morphology, micromorphology of the catalyst. And after synthesis, we get the butane, the powder of butane. And we use the catalytic testing equipment. There is the demo of the testing equipment. We use the nitrogen introduced from here and inject the ethanol from here. And then we mix in the vaporizer. The vaporizer is 100 Celsius degree. And then we introduce into the reactor. The reactor is the fixed bed. The catalyst is here. And then we get the product here. And we will analyze the product by GC. And let's see the catalyst characterization part. We synthesize the MOF and the beta zeolite. So we see the signal, both the signal are on the XRD. And after pyrolysis and calcination, the MOF are all converted to zirconium dioxide. It shows that our MOF are all transformed to zirconium dioxide. And the SEM and TEM also show the same result. We can see that some crystals on the dealuminated beta. And after calcination and after pyrolysis and calcination, the crystals are still here. And we see the TEM. The TEM is more clearly. We can see the crystals, the large crystals on the zeolite. And let's see the catalyst performance. Without the zinc, all the product, most of the product is ethylene. The black is ethylene. And we add a 0.8% zinc. The main product become butadiene. And in the 18 hours catalytic test, the butadiene selectivity is very stable. And our catalyst performance, the ethanol, in the 18 hours, the ethanol conversion is 93.9%, and selectivity is 65.5%. And after the test, the catalyst become black. We just use 550 Celsius degree. The catalyst become white. It can be regenerative. Thanks for your attention.
Okay, yeah.
thank you for your presentation. Yeah, since high temperature heating is required up to 600 degrees as reported in your presentation. So my question is, how much energy do you need to get your work?
The catalyst?
Yeah.
To get a catalyst?
Yeah.
How many minutes energy?
Yeah.
Oh, I
The
didn't.
heating process is within 600 degrees.
Yes,
Yeah,
in the catalyst produce process,
Yeah.
You need to heat to 600 Celsius degree. We don't, because the catalyst production, you don't need to always produce the catalyst, because the catalyst can be regeneration. So we don't calculate the energy.
Okay.
I think you are doing a very good job. But
Thank you.
in your the title is the breakthrough in the biomanual conversion technology. Can you point out where is the breakthrough in the system?
Yes, it's a very good question. Because the other catalyst, they don't use their large zirconium dioxide. They use very small particles, but we want to adjust the microstructure. So we use the mold to create very large crystals.
But that's for the catalyst. But you say the breakthrough in the conversion technology.
Breakthrough. Because the
conversion, you're just talking about the material, but conversion technology.
Yeah. Okay.
So the stability of the catalyst is good, right?
Yes.
Yeah, that's a breakthrough.
Thank you for your breakthrough. Thank you. Okay, we're moving on to team 15. Right, look at the camera and.
Yeah, okay, so I think in mechanics, as in a good movie, we show, don't tell. So let's try to show. So you can see here already that they are pretty much identical. Like propeller thing is just a technical thing, but basically they look the same. So the only difference, major difference, is the gear ratio between these two. So we're gonna show you how this works. Yeah, so you can see here that this car actually goes against the wind direction. It has high gear ratio. Yeah, so next one. Yeah, so this actually moves against, towards the wind direction. Yeah. Yeah, so I guess that's all that we can say. It just, I think it says for itself. And I think we can and we actually wanted to show once again the video with the treadmill, the actual proof of the fact why it actually moves faster than the wind. So yeah, as you can see, this treadmill actually runs there to the left, and the car would go to the right. Yeah, so you can see it goes to the right. So as I've told you in the presentation, actually it means, so if it would move only with the speed of the wind, it would actually stay in the same place relative to the terminal. But it goes in another direction. So yeah, this kind of, in a simple words, it's a proof that it really moves with the speed that is greater than the speed of the wind. Yeah, so I think we can show something more, or we can answer your question. This is just a simple toy that we can run through prep.
Yeah, because we will save time.
Yeah.
Smart students finished scientific part. Just how babies can use this machine. Sure, constructed machines, and after they and just after change only gear, because we change we say different gear. Yeah. Check and again.
Yeah, the different direction.
It's okay.
I finished. It's not the best. It's not the best thing to show, but yeah, the principle I think is clear.
Very good for health. Questions?
Yeah, questions.
Yeah, I think it's a very good innovation. My question is that for practical application, I think longing speed can be adjusted. It's quite important. How to control the moving speed of the vehicle. So do you have any idea, to adjust the brake relative to the streamline, the angle? Do you have any idea how to adjust or control the speed?
Yeah, so it actually has a limit, some limit value. So you just it gains some speed and then it goes with a constant speed. So
yeah, but I think you can add on, additional design to control moving speed. Then this innovation will have potential for practical application.
Yeah, of course. That's a good question.
Yeah, thank you for your presentation. My question is there any real application to the transportation vehicle for this concept?
As we showed, it can be used, for example, in gas pipes, but I think, for example, it's in deserts where there is strong winds. You can use it for transportation also, I guess. You just need to be, like, this will be an engineering problem. It's not the idea problem. So the idea is here, and the engineering is the different thing. But I think, yeah, of course, the idea could be used.
This is not the idea. This is the engineering.
No. The idea is that you can actually move against the wind and faster than the wind using changing gear, just changing gear, no redesign.
Agree.
Because of the idea
Yeah, of course.
Did you take your energy efficiency about this car? The idea could be used. This is not
Yeah, so of course the numerical experiments they will
I think should we have a different energy should be following the flow of the energy conversion should be high, but against the wind to do the transformation.
Okay. Good discussion. All right, thank you. Okay, we move on to the last one of the session.
Thank you. Okay, we move on to the last one of the session.
So, good afternoon, everyone.
So we are from Smart Biomaterials and Bioelectronics Lab. So our lab basically works on the self-powered devices used for energy harvesting and sensing applications. So the basic mechanism of triboelectric sensors, that when a contact or separation occurs between two surfaces, the charge transfer will happen and it will generate some voltage output or current output which we can use for different applications. Okay, so for today's presentation, here we are showing our triboelectric nanosensor, which is a self-powered based sensor which we will be using for detection of E2 molecules as a potential organic waste in the water samples. And yes, here we have collected our E2 samples, that is, we are taking as a organic waste, and here we have the air which will be helping us to separate out the water molecules. And further, when it will be flowing through our system, it will generate some voltage output that we are going to see from our skin. And the whole idea of our sensor is to make a very portable sensor, which we can also make it a very large scale, so that we can use it in a very user-friendly manner. That's what our whole target is.
So now I will tell you that how our project aligns with the self-development goal as well as net zero idea. So we are trying to detect E2. What is E2? E2 is a synthetic estrogen compound that are found in birth control or contraceptive pills. So nobody usually talks about it, but this is one of the harmful waste that comes out of households, and that is very harmful for fisheries and any aquatic type. It increases the BOD, that is biological oxygen demand, and it also causes stillbirths as well as not very developed fishes and any other aquatic animal. So let's start this. So what basically happens is the analyte molecule comes through from this, and air passes through this, and it contacts and separates. So through this sensor, what we have developed is a synthetic peptide. That peptide has a selective binding towards E2. So what happens when the analyte with the water comes out and passes through it, it generates a certain kind of output here. And again, the air passes through it so that the other molecules can pass through it. You can see it better in this video. See, as soon as the water passes, the change in electricity can be seen. So that's how, this is just a prototype, and that's how we try to develop a fully potential kit. Because the reason why we try to do this is right now any potential detection kit is tedious. It requires mass spec based skills to, so it's tedious and laborious. We need to collect water sample and then take it to the lab and then process it. What we are trying to develop is a self-powered portable device which can be used to detect any place, anywhere. For example, if we are going for after primary or secondary waste treatment, we can use it to detect harmful treatment chemicals like E2. And this sensor is for E2, but in future we'll be working on more on trying to make more sensors that can be used for other than E2, other biological compounds as well. So this is our thing.
You describe the potential application in industry.
So one of our potential applications for industries will be the, we can target for government institutions, because many of the institutions such as hospitals, and not in Taiwan but in other countries such as Vietnam, Thailand, many of these countries also liberate their harmful organic waste of hospitals and municipal waste to directly to the water bodies, where we can use our sensors to detect those molecules such as E2 or other organic waste which are present in the water bodies, which will be helping us to detect. Yes.
What's the advantage compared to the traditional method of water quality monitoring?
So the traditional method which they are using is mass spectroscopy based methods, which are quite having a heavy equipment and also need a laboratory setup to analyze those water samples. So here we are trying to make it a very low cost and scalable manner, and also does not require any other power source to detect those analyses. That's what our advantage, one of the advantages we would say.
This is one kind of microfluidics.
Yes,
but many microfluidics already exist. This kind of concept maybe, I think, already exists. question.
Yes. So
What's the new?
Yes. So the microfluidic sensors, which they have been or you have been mentioned, they are not showing any real-time data. Like so, here we can show like when we pass some of our analytes, we can directly detect the analyte at the real-time manner. So that's what, and also we can monitor those data in a remote manner. Like we don't need to stay around the system at all the time. That's what one of our advantages.
I see you still using a pump. Is it possible to use your head instruments? Just use your head to inject. Is it possible?
Yes, we can do that. Yeah.
Control initial some current into the device.
Thank you for presentation. My question is, you said you need the gold particles. Yeah, so my question is, what is the cost?
So we are synthesizing the gold nanoparticles that will be helping us to bind with the peptide, and we then broadcast our gold nanoparticles on the copper electrodes, which will be helping us to detect the particular analyte. Whenever we need some particular analyte to detection, we can functionalize our gold according to that, and that will be helping us for the detection.
All right. Okay. Finish. All right. Your time's up. Thank you. Thank you very much.
Judges to take the seats, and we are going to the next team. Number 17, please come to the stage for your presentation.
Hey, hello everyone. My name is Tori Wang. We are group number 17. And today I want to talk about our research development and application of inorganic aqueous reactive cooling coating. And due to energy consumption crisis and global warming, we urgently need a sustainable technology. The PDRC technology can achieve the sub-ambient temperature by reflecting sunlight and emitting heat into the universe through the atmospheric windows, and without energy consumption and pollution. However, the most traditional reactive cooler has disadvantages such as a high cost, complex process, and limit the compatibility, which limit the large scale portability. So in this study, we developed a pen-like reactive cooler. They can offer high compatibility, stability, and hollow cost, making it easy to apply to various cooling applications. But most organic coating often release the amount of VOC. So in this study, we focus on the inorganic coating. And in this study, we selected styrene silicate because they have high transparency and high information and compatibility. Most it have the cost effective. And in this study, we focus on the four main experience design. First, we advertise inorganic particle, and we prepare the slurry and we coating on the coating to fabricate the reactive cooler. And finally, we use the device to test the cooling performance. As a result, we can see in this study we use console simulation and ball milling process to advertise the zirconium dioxide particle. As a result, we can see the zirconium dioxide can achieve 98% solar reflectance and 0.92% emissivity, outperforming the low zirconium particles. And because we want to increase the hydrophobic of the styrene silicate, so we use the NTNs and British acid to enhance the hydrophobic of the styrene silicate. As a result, we can see we can use these two chemicals to enhance the hydrophobicity. And due to the, you can see our coating can achieve significant soil reflectance of 94% and emissivity of 0.90, outperforming the commercial coating. So they can maintain it can achieve the high cooling ability even under the direct sunlight. And we use the outdoor cooling power tester. So you can see our coating can achieve 9.5 degrees Celsius even under direct sunlight and high humidity. And our coating can also achieve the cooling power of 72 watt per meter square, outperforming the commercial coating. So now they can see our coating just only have 80 gram per liter VOC content, significantly below the organic coating and EPA standard. And our coating 1 year can amount as a safe energy consumption about 207 kilowatt per meter, and the CO2 emission. So we can see our coating can very easy to apply to various structures by using a simple method. And our coating demonstrates outstanding pencil hardness and anti-solid property. They can see they can higher durability. In summary, our coating can achieve high reflecting and emissivity, and our coating have a lower VOC content and eco-friendly coating. Okay, this all of my presentation. Thank you for your attention. Thank you.
Number 18.
Okay, good afternoon, everyone. My name is Amir, and today I would like to share my research idea with a topic from greenhouse gas to green fuel, plasma catalytic dry reforming of methane for closed carbon cycle liquid production. So, as we know, the greenhouse gas is drive for climate change, and in 2019, CO2 made up 75%, followed by CH4, 18%. And both of them is the major greenhouse gas with atmospheric lifetime and global warming potential. So reducing CO2 and CH4 is required huge economic and structural change in energy and also transport and industry. So we need to develop a new technology to solve this problem. So according to IPCC, the global temperature should be limited to 1.5 degrees C. So, followed by this agreement, Taiwan have some strategy to achieve net zero transition in 2050. One of the strategy is apply CCUS, carbon capture and utilization. However, apply CCUS in Taiwan is challenging due to some geological factor. Moreover, we have some solution is CCU, carbon capture and utilization. They can convert CO2 and also convert CH4 into fuel or valuable product. So dry reforming of methane is one of solution because they have some advantage to convert two major greenhouse gas into the hydrogen and also carbon monoxide. Moreover, its potential also to generate liquid product and easy to store and transport. So far, based on the thermodynamic equilibrium, 50% of CO2 and CH4 can convert into carbon monoxide and hydrogen at high temperature. However, if we focus at 100 and 200 degrees C, they can generate a methanol and acetic acid. Recently, methanol is high demand in industry because they has several advantages. So to improve the selectivity of methanol, we need add catalyst to accelerate the methanol selectivity. So our solution is a combination between plasma and catalysis, especially for non-thermal plasma. So how it works is CH4 from the source and CO2 from the source, and move the separation and capture and go to the plasma catalysis to generate carbon monoxide, hydrogen, and methanol. After that, they use for fuel and industry. And the emission is recycled to the plasma catalysis. So it called carbon closed system. So to evaluate our idea, we do some short preliminary result. First, we evaluate by the catalyst preparation, followed by this step, and then catalyst characterization. And after that, we put the catalyst into the discharge zone and evaluate the conversion, energy efficiency, and also the selectivity. And for first investigation, we do some evaluation for non-thermal plasma without the catalyst. And we evaluate at different effect flow rate, ratio of CO2 CH4, effect frequency, and also apply voltage. Overall, we conclude that optimal reaction condition for generate liquid byproduct is ratio 1:1 with the resident time 5.6 seconds. And frequency 18.5 and also the apply voltage 12.5. And after that, we apply a catalyst, ferric nickel with aluminum oxide. So far, we can achieve the conversion more than 50%. And methanol selectivity 46% and energy efficiency 0.42 millimole per kilojoule. However, it's crucial to evaluate more deep before we apply into the practical condition in industry. So we made some performance metric like should be achieved conversion more than 60% with low temperature to improve energy efficiency and also minimize soot and coke formation in the catalyst, improve the selectivity of methanol at least 50%, and also evaluate the durability, mechanism, and also economic feasibility. Hopefully, after we evaluate more deep in this plasma catalysis system, we can have benefit into environment, energy, economic, scientific, and also social impact. So our conclusion, plasma catalytic dry reforming of methane is smart part for convert two major greenhouse gas into the green fuel with a closed carbon cycle. I think it's end of my presentation. Thank you.
Thank you. Now we're moving on to the next presentation, team 19.
Good afternoon, respected judges. Our research is focused on the significantly focused to the. Good afternoon, respected judges. Our research significantly focused to the.
声音可以调大一点吗
Okay. Okay.
Could you come closer
Okay.
to your mouth?
Good afternoon, respected judges. Our research significantly focused to solve the two major problems in the world. Focuses two major problem in the waste overload and the water scarcities, and the coal fly ash one have the most biggest waste overloads to problem to creating the achieve the net zero emission 2015. So coal fly ash will be the generating from the combustion of the coal from the thermal power plant. In considering in the Considering in the Taiwan, the 37% of the using the coal fly ash to generate the electricity, and two of the most popular countries, India and China, they use 48% of electricity generated from the thermal power plant. They use a lot of the coal to produce the coal fly ash. One of the biggest problem coal fly ash was the disposal and the waste overload in the world. So we try to use the so biggest problem in the disposal and the contaminant in the wastewater in the water and the environmental pollutions. So go to the air pollution, and then can be not if you not be control the dispose and the maximize to use the coal fly ash in the world, it can be the go to the it can be not go to achieve the net zero emission 2050. So this one coal fly ash can be the directly effect to the environmental and the disposal problem. So thus in the coal flyers and they use the ceramic membrane in the previous many research have been done by using the conventional method. Conventional method can be not have a fail to use the maximize the ceramic coal ash to make the produce the ceramic membrane. And then the biggest problem for the disposal. So 3D printing have the one of the best options can be used as the material of the CFA to make the ceramic membrane. But problem of 3D printing have a specific material like silica, alumina, zirconia applicable. But coal flyers here is a mixture of the different compound. It's not easy to print the can be not use the ceramic 3D printing can be print. But in this research we successfully develop one of the recipes to can be print the ceramic membrane by using the 3D printing. Why is the 3D printing the best options to the making the ceramic membrane? We can be the make the mass production of the ceramic membrane and can be reduce the disposal concerning of the coal flyers, and we can be develop the many structures of the ceramic membrane. And the ceramic membrane, this is the formulation of the ceramic membrane of the from the coal flyers. We can use the 3D and the different other structures. After the use the coal flyers and the different materials, we check the economical feasibility. Coal flyers we cut the 71% of the total cost of the other material. Like zirconia, the silica have a highest cost compared to the in the market, but CFA is a very low cost. We can be 71% of the total cost of the ceramic membrane. And the second one, we use the application of the coal flyers membrane from the different field like liquid separation and the solid liquid separation and the electricity generation. So we go to the electricity generation. So in the Taiwan have a biggest problem with the IPA. IPA removal from the IPA from the semiconductor companies. We use the ceramic membrane of from generating from the CFA. We remove the 88% from the IPA from the wastewater on the industry, and further we go to the textile company. So we check the total around 98% of the removal of the total from the color from the dyeing wastewater, and further we go to check the feasibility of the ceramic membrane in the temp fuel cell and the microbial fuel cell, because until the microfuel cell have used the commercial membrane is called the Nephon, which is a very costly, and 38% have to use the total cost of the Nephon of the MFC. So that's why until now though have no any membrane can be replaced the Nephon membrane. So we develop this ceramic membrane can be replaced the alternative of the Nephon. Nephon is one of the most PFAS ceramic PFAS membrane. That can be damage the environment. So that's why this ceramic membrane have a PFAS free. 100% use the coal fly ash to generate the electricity. And then we check the total operating cost around the 37% of total cost, reduce the total cost of that part. And then we can see the total voltage. We get around 720 millivolt compared to the Nephon. We can see we got the total 4 volt, just few of a use the micro fuel cell. And then further we go to the possibility, further go to the mass scale, we go to the TRL5. Until have we done the TRL4, so we go to TRL5 for the filing the patent. So we go to the further application for the scale up.
Thank you. Now we come to the final presentation delivered by team number 20.
Test.
And this team could be our last. After this one, we are going to a demo site. So, team 20, please.
Hello, distinguished committee member, teacher, and friend. We are a group 20. Today, we will be introducing the integration of innovative cost-away energy and the carbon negative cement material with a supercapacitor energy storage system to achieve net zero goals. Here is our outline. After introducing our team member, we will explain our motivation for designing the CWEC. In the project overview, we will present our system, and finally, we will discuss the various benefits our system can achieve. We are a team comprising of individuals from diversity field, including the PSSN, EE, and the AA. Our motivation stems from ocean energy. Europe prediction that wet energy has great development potential. Taiwan reached in ocean energy target 1 megawatt marine energy capacity by 2030. Our project aims to harness this potential, advancing Taiwan's transformation and supporting global renewable energy goals. Our project integrates 3 major components: coastal wave energy converter, CWEC, supercapacitor energy storage system, SESS, and the carbon negative cement. The CWEC consists of 6 parts, including the generator, hydro turbine, blade, base, supporter, and the carbon negative channel. After several experiments, we found that a 19-centimeter channel pairing with a 30-degree angle generated the most amount of power. There's a huge difference between our project and the oscillating water current, OWC. CWEC boosts efficiency by reducing energy conversion stage. We adapt 2 rectangular planes beside the turbine blade to guide more water into blade area. The design improves wet energy by increasing water impact on the blade. The blade enhances power output with a 6-centimeter line performance bed. It achieved optimal balance between foregardency and the energy conversion stage. Since wet energy is intermittent, we deploy the SESS to store energy. Compared to lithium battery, its rapid charge discharge, longer lifespan, lower pollution, and safety come in handy for the CWEC. When the wave energy is in the generation cycle, and the generation power meet grid code, allowed the supercapacitor to store energy. When the generator energy exceeds storage capacity, the system will residual power mode, enabling potential future hydrogen production. If the generator power does not meet grid requirement, the system will initiate the first discharge stage to compensate for the deficit. However, when the wave decides stop generating power, the system will enter the second discharge and release entirely on the supercapacitor X power supply. We optimize the power supply stability by minimizing the loss of power supply probability during simulation. To practice the device, we adapt a short-term wave energy power forecasting model. If the forecasting model wave height exceeds twice the height of the device, the system will temporarily shut down and wait for the next data update. The carbon negative cement can absorb carbon by incorporating 30% of biochar. It lets waterproof and boosts superior durability and 3D printability. Due to CWEC is simple structure, construction CWEC requires 72% less cement and 17% less gravel in the OWC. The carbon footprint of CWC is significantly lower than traditional OWC, from 21 ton to 17 ton carbon emissions. Taiwan coastline has the 10,000 megawatt potential wet energy. By deploying CWEC, carbon absorption can be requirement to 2,618 7,000 forest park. Taiwan has 10,000 megawatt potential marine energy, and deploying just 0.1% of equipped generator green energy benefit 4.39 billion NTD. There are 2 million tons of dollars in Taiwan. If we replace less with carbon negative cement, 1.8 million tons of carbon emission be reducing. Thank you for your listening.
Thank you. Thank you very much. Okay. Now, after the final presentation, the dear judges will move around for the demo site to the last 4 team demonstration and explanation, please.
Hello everyone, I'm Team 17. Today I would like to introduce our project and passive cooling film. And in our film, we can see we put on the sample, we put sample on the top of the polystyrene box. And the reason we choose the box is polystyrene can exclude the heat conduction, as it means the change of temperature came from the reflection of our sample. And when the light shine on it, our sample can reflect all of the heat. And it means the less heat will go inside the box. And in our test, we use the lamp, and we can see our coating has a lower temperature and compared to the commercial. And it means only use the reflection, and our coating have the good performance. And in the future, if we use our coating on the outer layer of the building, it will definitely works too.
Yeah, so Mingwei just tell us about the effective of cooling, and now I want to demonstrate the outdoor durability of outdoor application. And as you can see, this is our coating on the different surface, and it adheres very well. And it shows that have a high competitive of different substrate. And this is a standard device for the hardness test. And commercial coating typically can reach up to only reach up to HB, but to our coating we can reach up to 6H, and it's just because we choose using of inorganic materials, which has more durability and more stable compared to the commercial organic materials. And because of the strong adhesion and the strategy resistance, our product have longer product lifetime, which is not only reduce the energy consumption, but also has a lower labor or material and the manufacturing cost.
In this part, we will show the hydrophobicity test compared to conventional coating and our coating. And first, this is commercial coating. And when we drop the water on the conventional coating surface, you can see the water stay on the surface. And the other one is our coating. When we drop the water on the surface, we can see it quickly roll off the surface. And this shows our coating has much better hydrophobicity than the conventional coating. And that's all.
Do you compare with SiO2? Many people use SiO2, right? You know that?
Yeah, actually, we compare CO2 because why we choose the colonial dioxide, because the colonial dioxide is the radiation index more than
smaller than the silicon. So they can enhance, you can engage.
What's the price? Many people use the SiO2.
Yeah.
But they think but still it's too expensive for real application. That's the problem with SiO2. But I think your material still face the same problem. Like, do you consider this kind of problem? I know SiO2. And your university also study the SiO2.
We talk about the cost. I think because we product have longer lifetime, so we can have a cheaper cost in each year.
Yes, let me see. Because the SiO2, the refractive index is the same as the sodium silicate. So yeah, so in this study we choose the zirconium dioxide because the zirconium dioxide, the refractive index.
Yeah, maybe the performance maybe better than better, but the problem is that you use how to coat on the surface. Yeah.
That's better.
We choose the same method.
You use the bread, but another area.
Maybe we can try. Yeah, our binder is solid silicon. So yeah.
Anyone else? Okay, 4 seconds, 3 seconds, 2, 3. Thank you. All right, let's move on. Thank you for your response. All right, now we go to the unit number 18.
Good morning, everyone. Good afternoon, everyone. Welcome to INTL 18 group, and I am Ruth. We will more deeper to introduce about our system, from including why we choose the gamma aluminum oxide and how to combine with the plasma, and the system of our lab scale. Start with why we choose the gamma aluminum oxide, because gamma aluminum oxide has the high surface area, and it can provide more active site to enhance the efficiency of convert CO2 and CO. And in the previous study shows that it has a good efficiency about dry reforming of mindset. And in this picture we can see the nickel and the iron has a lower price and a lower global warming potential advantage compared to the other metals. So we will coating the iron and the nickel onto our support gamma aluminum oxide. After preparing our catalyst, we will combine to our DVD reactor. The DVD reactor uses the cross tube and the inner electrode and the ground electrode. And as we can see in here is our lab scale, the DVD reactor. We will have the inlet gas flow from the upper, and we will have the outlet here. And as for the power supply, we use the DC power to provide the discharge, and use the AC power to change the frequency, and use the oscilloscope to monitor our applied voltage and the current and the power. And we can see during discharge we will see the glow discharge like the purple light in here. And here is our lab scale system. we use the pure methane and the carbon dioxide, and use the NFC to control the flow rate and the mix together and into our DVD reactor. And in the outlet, we have the water base. We will have a liquid trap inside the water base. We will use a lower temperature to make the methanol STSA and the ethanol to change to the liquid form and collect them. And then the outlet of the liquid trap, we will use the GCTCD to detect the gas phase like the reactant, CO2, CH4, and our gas product, CO, hydrogen, and the C2H6. As for the liquid product, we will use the GCFID to detect them. And I want to say more about why we choose the iron. It's because iron can provide the active site to make the methane be dehydrogenation. And for the nickel, it can make the CH3 group combine with the OH group to form the methanol. The group of iron and the nickel, it will help the methanol to be, selectivity will be higher, and the carbon decomposition will be lower because of the synergy between iron and the nickel. And as for in the future, we will use scale out to the industry scale. So we will use the ceramic catalyst and combine with the tube like this one. And put the catalyst into this tube, and we will have the several tubes at the same time. And the discharge, we can discharge at the same time, and we can treat the CO2 and the CH4 more than compared to our lab scale, and help the methanol selectivity more high. And that's all about our system. Thank you for your listening.
So you use a plasma as a reaction. Using those particles, it seems that the plasma will be hindered. So energy density will be lower down. So how do you solve this to make it uniform conversion?
Is unique question. So far as I know, it's difficult to adjust the discharge uniform from the upper to the lower. So one of the solutions is modify the dielectric constant, surface area, and also the electrochemical property of the catalyst by reduction of hydrogen, so the oxygen is reduced to provide more active site or even the electric constant surface area. So I think this combination, because it's still under development stage.
So the utility, the utilized service of a catalyst is really not that much.
Yes, it's combination between surface area and electrical property of the catalyst, like the electric constant.
I have a question. You just mentioned your system is the data system. How to scale up? What kind of problem you will face?
Well, the problem is, so far is DBD has problem for the total flow rate. For the scale up, maybe need combination for series and parallel to solve the flow rate, higher flow rate. Yeah. So far they just use for 50, 100 or 200 milliliter per minute.
Excuse me, time's up. Thank you, guys.
Thank you.
We use the full-fly membrane for the various applications, from the pre-operation, application, and the microfluid cell. So 3D printing is one of the most important good options to make a saving membrane. Other commercial membrane has to not be commercialized as a mass production, and we cannot be designed the different structure. So this time is like a commercial ceramic method is a fail to use the mass production or the full size fabrication and reduce the disposal. So
In this case, we use the different applications as a use of like cold fly ash and the cold bottom fly ash. Cold bottom fly is very hard to convert in the powder. So we in the formula to convert the cold bottom ash and the cold fly ash. The different parts. Now currently the ceramic membrane use a single compounds like zirconia, alumina and other compounds. But the cold fly is the mixture of the different compounds, so very hard to in the 3D printing. We are successfully derived the ceramic slurry to can be printable. So this time we print the different kinds of membranes. Like one is the like non-pattern and the pattern membrane. The pattern membrane have good options because reduce the material cost and they use the high removal efficiencies and give the more surface area. So in this case we use the different kind of industrial wastewater like one is the isopropyl mixer wastewater come from the TCMC. We use the 85% of the IPA from the wastewater. And then we also use the azotonic industrial wastewater as a use in the microfuel cell. So microfuel cell have the energy positive system, but in the problem is in the system they use the protection membrane. Protection membranes are mostly use the nephia. Nephia is very high cost and around the 170 meters USD per meter square. It's very hard, very costly. And the total cost of the whole production of electricity 37%. And the second thing is a very toxic is a mixer the PFAS and this part PFAS membrane, and that's why we are going to give the alternate membrane in the world is the use of replace the ceramic membrane is the nephia. We see the nephia membrane have a cost around reduced around 33% of the total mass of the product. So we use the 4 system, and each system have a value 250 ml. We can generate the voltage around 4 volts, and we can see the electricity we generate. Without this one system, we can generate the electricity and simultaneously produce the wastewater, clean the wastewater, and then. And the second thing, we have to go in the lab scale. The lab scale have to done for the produce the electricity forward. And we are go to now looking the PRL5. The lab scale is the pilot program. So that's not.
Thank you for your presentation. My question is, you use 3D printing to make the surrounding membrane. I always think that the structure of the membrane will affect the performance of the system significantly. But you could not mention, that you use the 3D printer should be, try to construct the best structure of the membranes. Can you comment this?
In this first case, in this research, no one has done it to use the cold fly ash to make the 3D printer. Because the cold fly has a mixture of the many compounds, like silica and other things.
Why you use the 3D printer?
3D printer?
The 3D printer should be, construct the structure.
We construct the structure with the whole. Important thing of saying here, because of the cold fly is a mixture of the compound. It is not a single compound. Mostly the 3D printing applicable is a single compound, like alumina, it's a homogeneous compound. The cold fly is not a homogeneous, it's a heterogeneous. We cannot control its property. If we know the property, alumina is the same. No, this is cold fly. No. This is the cold fly. This is a mixture of the compound. It's a mixture of the cold fly.
But usually you should make some structure.
Yes, this is honeycomb structure.
Honeycomb structure.
Yes.
Okay, use the honeycomb structure.
So the main important thing is here, cold fly is a compound of different compounds. It's very hard to control the rheology. Because of single compound, we can control the rheology, but to mix up the compound, because cold fly is a mixture of different compounds, it's very hard to control the rheology. We successfully developed his rheology. We can fabricate the mass production rheology. Important things,
we can control the disposal, and we convert the different mass production, and we control the different characteristics of the membrane.
You already mentioned the important is the composition of the edge waste.
Yeah, yes,
it is wearable product because you cannot control the quality of the member.
So that's why, Professor, we control the properties. So go to material processing. We go to material processing. Material processing, we control the property of the origin of the CFA. Because CFA will be property will change according to its place. Because if I go to Taiwan, I can collect some cool flares. I go to China, they collect different. Property is different.
Different source.
Different source. So we go to further material processing. Material processing will give you the particular ratio of the compound. Like so, if we can go to
you should check it.
Yeah.
All right. Okay. Thank you. Thank you for your explanation. We'll come to last one. All right. We are ready to go. Yes.
Hello, judges. We are International Team 20, and it's our pleasure to share our innovative idea with you today. Let's begin with something we often see along Taiwan's culture. This is not an alien spaceship. This is wave break or called heteropod. Yeah. Its job is to reduce the wave impact and to protect our shoreline. As you know, Taiwan is surrounded by the ocean and have many wave break, which means we have huge potential to develop wave energy. So what if we turn those wave break into power generator? That way we will not only protect our castle line, but also we can create clean energy. Now let's show how can we make that happen. This is our second generation generator, CWEC. It's built with a carbon negative cement channel and a generator with our new design blade, integrated with our supercapacitor energy storage system. By using our full control strategy, when the wave comes, the channel correct the wave energy and driving the generator to generate green electricity to charge our LED light and storage the energy into our supercapacity. And when the wave starts, the supercapacity discharge and start to release its energy to our LED forwards. Right now, let's watch our demo. When the wave comes, it pushes our blade and driving our generator to generate the electricity. And at the same time, the supercapacity is charging. It's also charging. When the wave starts, the supercapacity discharge and start to release its energy to us. So the LED keep lying. With this design, we can achieve 4 goals. First, we still can protect our castle line. Second, we can develop green, sustainable energy. And most important, the energy storage. Yeah. The third is carbon reducing, which will reduce more than 23% than traditional OWC system. Moreover, we can make our cathode line more beautiful. Thank you.
Thank you for your presentation. As we know, the supercapacitor is well known, to be used in the wave energy. Can you elaborate, the detail, what's your contribution or what your breakthrough this year compared than before technology?
Okay, breakthrough. Display.
Okay. Last year we have just played on turbine, and this year we add two planes on the blade side. And the reason is we want to improve the incoming fluid volume. We can see the equation. P equals the energy P equals tau token multiplied angular velocity. At the same angular velocity, when token increase, the power will increase too. And from Navier-Stokes equation and angular momentum equation, we have equation 5. We can see the token and the volume. Token is proportional to volume. So when we improve the incoming fluid volume, the token will increase, and token increase, the power will increase too.
The total 6 minutes is up. Now I suppose we'll get longer, so we have to make a pause. Okay, but thank you very much for your explanation. And dear judges, we may go back to our seats. Thank you. Thank you very much.
All right. Now I'm going to announce for international contest division. We just complete the 20 competing teams finalized, including the presentation and demonstration. I really appreciate it, all the endeavor put by all the students and the teachers. And also our judges are gonna leave for the evaluation and make assessments about your previous performance. And the result will be announced at the closing ceremony. So it will about take another 1 hour, and that's a very important job. So, okay, since they are leave, but I would like to make an announcement later. Ladies and gentlemen, in the international contest, I think you just complete the whole process. And now we have several things. First things, if you do not vote for the best popularity award, now we can still open the slot for until 3 o'clock this afternoon. Because now on my watch it's 2:33, so by 3 o'clock p.m. you can still take a vote, cast a vote. Now we show the current status of right over here. Again, on the very right-hand side, there is the rank from the 40 to 31, and you can check the team number, including the Taiwan and internationally. And that's the final score here. Okay, we move on to the previous page. It's ranked from 21 to 30. Okay, and we move forward, it will be team 9 now in the 11th place, and 12th place is team number 8. Okay, check the first top 5. Okay, you can see the top 5 right over here. Taiwan competition number 15, now currently ranked number 1. And number 2 would be the Taiwan team, number 13. And this is final score. Wow, it has a very obvious leading at this moment. But still, we still have possibility for changing if you vote for specific team, taking the opportunity in the last half hour. So it could change. Okay. Now later, in addition to taking the cast the vote, you can also have a souvenir watching, because once again, you would have the opportunity to win the 65 items as a gift. Today, in the center part of the auditorium, we have a selfie picture taking by our staff. You can leave your beautiful faces with your friends. Even the friends you just know today, you can go to our booth. That's the free photo booth. They will take care of you for a great memory. Now the theme color, the very green color, will be as a beautiful background. So take as many pictures as you can. And now it's a free time, but I would like to invite you come back at the about 2:55, which means 5 minutes to 3, because at 3 o'clock we're gonna have a closing ceremony and award ceremony at a time. A lot of information will be released and announced at that moment. So every team, you can sit by your team number, and together, if you heard your name or see your team name on the stage, on the screen, that is you. You can step forward very fast from my left-hand side and come up stage to stage, because you will be highlighted at the moment. Okay, so now it's a free time. You can do the free networking, exchange some contacts for the future cooperation and networking. So now time is yours. Thank you.